Amidst the profound silence of deep space, traversing the immense starless chasms between galaxies, a solitary traveler glides through the cosmic void. This entity is neither a star, nor a planet, nor a conventional comet, but possesses a mystery far exceeding these known forms. This visitor, bearing the designation 3 Atlas to astronomers, had journeyed for an unimaginably vast duration measured in billions of years. Its passage spanned the darkest expanses between stars, following a singular, unwavering course that defied ordinary cosmic mechanics. Then, on the 29th day of October in the year 2025, this interstellar wanderer, named 3 Atlas, achieved its closest approach to our own sun. This pivotal encounter presented a profound challenge, questioning established notions about objects originating beyond our solar system. From the very outset of observations, 3 Atlas defied all conventional expectations. Unlike the comets residing within our own solar system, which exhibit predictable patterns of increasing brightness and activity as they draw nearer to the sun, Atlas manifested behaviors that simultaneously captivated and unsettled the scientific community. Its trajectory was not merely hyperbolic in nature, it was distinctly alien. Calculations meticulously placing its point of origin far beyond the confines of our local stellar neighborhood. Every measurement collected, every fragment of data scrutinized, seemed to softly suggest that this was no ordinary object. It evoked the sensation that the universe itself had attempted to convey a message, yet one inscribed in a cosmic language humanity was only just beginning to comprehend. The earliest telescopic images captured something incredibly faint, almost imperceptible, a mere dim streak adrift against the vast star-studded backdrop of space. Yet even within this subtlety, Atlas clearly signaled its fundamental difference. Its initial brightness, appearing almost negligible at first glance, commenced an increase at a rate that was already proving unusual for a comet situated at such a considerable distance from the Sun. By the time Atlas traversed the vast expanse beyond Jupiter's orbit, astronomers worldwide began to detect subtle anomalies in its behavior. Initial observations of its light curve revealed inconsistencies that immediately suggested a complexity far exceeding that of a simple frozen solar system wanderer reflecting sunlight. The patterns indicated structure and perhaps an underlying organization that conventional models for such bodies struggled to adequately explain. Recognizing the profound significance of these early hints, ground-based observatories across the globe and powerful space telescopes simultaneously shifted their instruments towards the enigmatic object. Researchers from every inhabited continent mobilized with intense urgency, seizing every available moment to gather comprehensive data. Analysis of its trajectory, its delicate and evolving color shifts, and the intricate manner in which its diffuse coma scattered sunlight all converged to suggest something fundamentally different at the core of Atlas's nature. Unlike the comets familiar to our telescopes, Atlas seemed to exhibit a peculiar vitality in its actions. It interacted with the sun's energy, yet not in the slow, predictable fashion we had long associated with such objects. Its response was dynamic and rhythmic. It pulsed with variable intensity. It shimmered, displaying fleeting changes in brightness and texture. It hinted, through these behaviors, at active processes unfolding beneath its surface, processes operating on scales and in manners that baffled immediate scientific identification. Even more profoundly puzzling were the very first spectral analyses conducted. The light signatures captured from Atlas bore no resemblance to the characteristic profiles of comets we know. Typically, as a comet nears its closest approach to the Sun,
It releases predictable volatiles, water vapor, carbon monoxide, and a standard suite of organic molecules. Atlas, however, presented spectral lines that pointed towards far more complex chemical compounds. These included evidence of extended carbon chains and nitrogen-rich molecules, even fleeting hints of unexpected chemical radicals, highly reactive fragments previously unanticipated in such an environment. Scientists, initially skeptical, intensely scrutinized their computer screens, double-checked all connections, and meticulously recalibrated their sensitive spectrometers, searching for potential errors or interference. Could these astonishing readings be flawed? Each subsequent test, each independent verification, instead confirmed the same extraordinary and perplexing narrative. The evidence was irrefutable. Atlas defied easy categorization. This celestial traveler was unmistakably alien, its chemical signature betraying origins far beyond the familiar embrace of our solar system. It hailed from realms never directly witnessed by human eyes, a profound distance etched into its very composition. The intrigue deepened dramatically as scientists turned their attention to its spin. Most comets exhibit a deceptively straightforward rhythm, their rotational periods steady and discernible. Atlas, however, defied such simplicity. Its axis seemed to dance with subtle, irregular wobbles, an unpredictable ballet. At times, its rotation appeared to complete within mere hours, only for fleeting shifts in luminosity to betray its complex face-on presentation. This shifting perspective hinted at a form sculpted by influences beyond our current comprehension. The magnitude of the mystery became overwhelming. Here was an object that had traversed unimaginable eons, enduring the relentless assault of interstellar radiation and the profound isolation of cosmic voids, finally arriving in our solar system.
Yet its behavior was utterly unprecedented, a spectacle no human had ever encountered. Astronomers quickly grasped that Atlas transcended mere strangeness. It represented something entirely unique, a cosmic anomaly. Dr. Chi-Chang Jiang, observing from Lille Observatory, recalled the initial moments of discovery as standing precariously at the threshold of understanding. It felt like gazing out upon an immense, uncharted wilderness, brimming with profound uncertainty. Carl Badams, affiliated with the U.S. Naval Research Laboratory, resonated deeply with this sentiment. He noted that every fresh influx of data seemed to unlock more profound questions than it resolved. How could an entity forged around a distant sun exhibit such erratic, unpredictable motion? What mechanisms allowed it to endure the relentless bombardment of billions of years of cosmic radiation, a force that typically disintegrates such fragile bodies? The answers remain shrouded in the vast, silent mystery of space. The very surface of Atlas concealed mysteries, hidden even from our most advanced scientific tools. This profound uncertainty ignited a palpable tension within the astronomical community. While the arrival of interstellar objects isn't entirely unprecedented in scientific history, very few have yielded the extraordinary volume of data currently streaming in from Atlas. Its remarkably close approach to our own sun presented an unprecedented window to observe an object literally forged in the furnace of a distant star system. Yet this unique opportunity was inseparable from a growing sense of frustration. The more we discovered, the more starkly it revealed the boundaries of our current scientific models and the fundamental assumptions we held regarding the behavior of comets, and indeed the very nature of matter within the most extreme cosmic environments. By the time Atlas had traversed its way into the inner reaches of our solar system, a small but rapidly expanding cohort of dedicated scientists began to grasp the immense significance of this event. This was far more than a chance to witness a comet brighten as it neared the sun. It had become a grand experiment orchestrated by the universe itself, with humanity cast both as active participants
and astonished observers. Observatories scattered across the globe coordinated their efforts seamlessly, sharing data instantaneously in real time. The internet pulsed with intense speculation and theorizing. Preliminary research papers were drafted even while telescopes and sensors continued to gather vital light. Each new observation seemed to amplify the dual feelings of profound awe and bewildering confusion gripping the scientific world. What resonated most deeply with so many researchers, however, was the subtle and striking elegance embodied by Atlas. Its form defied the expected chaos. Instead, there existed a distinct sense of symmetry. There was an underlying structure.
There was, quite literally, a story unfolding in its light. This stood in stark contrast to many comets originating within our own familiar solar system, which are often described as battered, irregular, and fragmented. Atlas, in comparison, appeared to carry the organized, almost purposeful history of its distant birthplace star system upon its surface, presenting a coherent narrative where others showed only disarray. Each flash of brilliance, each unique spectral signature, seemed to whisper tales of eons spent traversing the vast expanse of interstellar space. This celestial visitor, it appeared, was not merely a product of random cosmic events, but rather a being sculpted by the profound forces that shape the galaxy itself. Thus, even in the preliminary stages before its closest approach to the Sun, Atlas had already accomplished something extraordinary. It had captured the collective imagination of humanity, serving as a poignant reminder that the universe is anything but static. It underscored the transient nature of our models, our comprehension, and our quest for order, highlighting that these are merely fleeting attempts to grasp the enormity of what lies beyond our grasp. Above all, it served as a stark reminder that when an emissary from the stars makes its presence known, we are compelled to transcend the confines of our existing knowledge and encounter the extraordinary. By late October, as Atlas drew nearer, the anticipation within the astronomical community reached a pitch. Observatories meticulously prepared to monitor its trajectory, while space telescopes were assigned the crucial task of uninterrupted observation. Researchers, some of whom had dedicated their entire careers to the study of comets, were humbled by this anomalous object that defied categorization. The palpable excitement among them was interwoven with a profound sense of respect, evident in every report, communication, and calculation. 3 Atlas was not just another comet, it was a messenger from beyond our solar system, poised to impart lessons we were unaware we needed to learn. Even now, reflecting on those initial observations, one aspect is indisputably clear. 3 Atlas was never an ordinary comet. From the instant its existence was first confirmed, this celestial visitor presented a profound enigma, its layers of mystery only beginning to be cautiously uncovered. Each anomalous reading, every unforeseen surge of brilliance, every unique spectral fingerprint whispered of a narrative spanning billions of years. And that unfolding story, as astronomers would soon realize, was destined to take a trajectory far stranger than any speculative hypothesis could have foretold.
As the month of October surrendered to the closing days preceding its closest approach to the Sun, 3 distinct cometary nuclei drew steadily nearer, their collective path carrying them through the intricate architecture of the inner solar system with an astonishing degree of precision. This exactitude simultaneously ignited the excitement of scientific discovery and provoked deep bewilderment among the observing community. Every single measurement taken, each position meticulously plotted against the backdrop of distant stars, were subjected to exhaustive comparison with the well-documented behavior patterns of the countless comets humanity has cataloged over centuries. Yet Atlas persisted in its defiance, steadfastly refusing to conform to established expectations.
Even from a considerable distance, measured in several astronomical units, its divergence from the norm was unmistakable. Conventional comets exhibit a familiar rhythm during their approach. Their luminosity typically increases in a gradual, almost predictable manner, a direct consequence of the sun's intense heat, causing volatile ices trapped within their cores to transform directly into gas, a process known as sublimation. This escaping gas, accompanied by entrained dust particles, typically envelops the nucleus, forming a diffuse atmosphere called a coma. The interaction of solar radiation and the solar wind then usually sculpts this material into the iconic sweeping tail that becomes its signature feature. The visibility of this tail serves as a visible testament to the sun's profound influence. For decades, these consistent patterns have empowered astronomers to anticipate the behavior of incoming comets, to model their outgassing rates with increasing accuracy, and even to predict the formation of jets and potential fragmentation events. Comet Atlas, however, appeared to have fundamentally rewritten these governing principles, presenting a challenge to all existing models. Observatories scattered across the globe turned their attention towards Atlas with a level of scrutiny that had never been seen before. Using a variety of advanced tools, scientists began to gather a wealth of data about this mysterious visitor. Optical telescopes were tasked with monitoring the comet's brightness, tracking how it changed across different wavelengths of light. Spectrographs, meanwhile, analyzed the light emitted by Atlas, searching for clues in the form of molecular emissions that could offer insights into its composition. Radar measurements, another crucial tool, were deployed in an attempt to determine the comet's precise size and shape, providing a more complete picture of its physical attributes. Yet, despite these sophisticated methods, the most revealing observations came from space-based instruments. These satellites offered a vantage point that was impossible to achieve from Earth's surface, free from the distortions and interference caused by the atmosphere.
Instruments aboard SOHO, the Solar and Heliospheric Observatory, played a pivotal role in this analysis. Equipped with coronagraphs, SOHO was able to block the intense glare of the sun, allowing astronomers to observe Atlas as it ventured ever closer to the solar corona. The initial findings were, to say the least, perplexing. Unlike a typical comet, Atlas exhibited an irregular light curve. Its brightness did not increase smoothly as it neared the sun. Instead, there were subtle, almost imperceptible fluctuations. These were followed by brief surges and dips that defied standard comet physics. Analysts went over their calculations, double-checked instrument calibrations, but the anomalies remained. These peculiar fluctuations hinted at internal processes that were unlike anything previously seen in a comet originating from our own solar system. Space-based observatories added another layer of intrigue. GOE-9, a weather satellite that had been repurposed to observe solar phenomena, captured high-resolution images of Atlas during its approach. In the ultraviolet spectrum, the comet appeared as a faint, elongated smudge. However, its glow was uneven, further deepening the mystery surrounding this enigmatic celestial object. Certain regions on Comet Atlas exhibited unexpected brightness, while others displayed an unusual darkness, implying localized activity or variations in surface composition. Advanced stereoscopic imaging from the Solar and Heliospheric Observatory, commonly referred to as Stereo-A, enabled scientists to construct much more precise three-dimensional models of the comet's form. These detailed reconstructions definitively ruled out a simple spherical shape. Furthermore, Atlas also defied the image of a conventional, irregular lump of ice and rock. Instead, the models revealed an object distinctly elongated, bearing a striking resemblance to a cigar. Subtle contours and markings observed on its surface hinted at a complex, layered internal structure. Comparisons with the established behavior of typical comets proved profoundly different. In a standard comet, as its solid nucleus approaches the warmth of the sun, water ice embedded within begins to sublimate predictably at a specific distance. This process releases a cloud of gas, which, pushed by solar radiation and wind, forms a distinct tail. Simultaneously, dust particles are liberated and carried along with the escaping gas, creating the iconic, streaming trails that mark a comet's passage. Atlas, however, conspicuously lacked these conventional hallmarks of cometary activity. Remarkably, its expected tail, which should have been a prominent and easily observable feature by the time it crossed the orbit of the planet Mercury, was virtually absent. Instead, the comet material itself glowed with a diffuse bluish luminescence. This distinctive color suggested that the driving force behind its activity was not dust, but rather a significant release of gases.
The composition of these gases likely included carbon compounds and nitrogen-rich molecules. The behavior of Atlas seemed to fundamentally challenge existing understanding. It appeared as though this comet had created a form of activity previously unseen within our solar system, effectively rewriting the established rules. Astronomers swiftly turned their imaginations to possible explanations. Could the nucleus possess an unusual chemical makeup? Perhaps it contained a surprisingly high concentration of volatile ices. Or maybe its surface had undergone alterations through processes distinct from those experienced by comets originating within our solar system's familiar environment. Some scientists theorized that Atlas might possess a thin protective shell, a crust-like barrier that delayed the release of trapped gases until the comet ventured deep into the solar system's inner regions, where intense heat finally caused this layer to fracture. Concurrently, another hypothesis emerged, suggesting that the comet's distinctly elongated, peanut-like form could lead to uneven solar heating. This asymmetry, they proposed, might create localized zones of intense activity, explaining the comet's erratic fluctuations in brightness as different sections warmed and ejected material more vigorously than others. These competing explanations were subjected to rigorous analysis with each passing observation, yet fresh data consistently presented unexpected findings. Crucially, imagery captured by SOHO's specialized coronagraphs revealed that Atlas's coma, the luminous envelope surrounding its core, defied established patterns seen in comets skimming close to the Sun. Instead of forming a typical, symmetric halo encircling the nucleus, the emitted light appeared visibly stretched and distorted, aligned with the comet's long axis. This created a faint, ethereal glow that extended dramatically farther than standard models of icy material vaporization could predict. This pronounced elongation strongly indicated that material was being expelled from the comet in specific, directed jets, rather than emanating uniformly across its entire surface through gradual sublimation. Spectroscopic analysis proved just as perplexing. Initial readings in ultraviolet and visible light revealed exceptionally strong signals from carbon-based molecules, specifically C2, alongside significant emissions from nitrogen-bearing compounds, notably amidigan, NH2. While the presence of these molecules is common in cometary comae, the sheer intensity and the specific proportions observed were extraordinary. Standard comets typically exhibit a gradual strengthening of these characteristic signatures as they approach the Sun, correlating with increased solar heating. However, Atlas displayed these emissions at rates vastly exceeding what its estimated size and surface area would reasonably allow, creating a significant scientific puzzle.
In essence, it felt as though the comet had accumulated a vast reservoir of reactive material, which was now commencing to discharge in a measured, almost intentional manner. The chronology of these peculiar occurrences introduced an additional dimension of enigma. Their locations beyond 2 astronomical units. Most comets maintain a state of relative inactivity. Their ice remains solidly frozen. Atlas, however, commenced to display notable outgassing long before arriving at this crucial area. The observers were faced with a riddle. A body that was expected to stay largely dormant was already active, and its activity escalated in abrupt, unpredictable surges. By the time it had traversed the orbit of Mars, researchers understood they were witnessing something entirely unprecedented. The atmosphere within the astronomical community was charged with excitement. Publications and internet portals were abuzz with updates and preliminary examinations. Groups worldwide were collaborating to capture each photon, every variation in luminosity, every spectral signature. Conferences and private dialogues were filled with discussion. Could these irregularities be illusions of observation, or was the cosmos truly offering us a glimpse of a behavioral pattern previously unencountered? Most scholars incline towards the latter perspective. Atlas was not merely eccentric, it was a trial to our comprehension of how substances behave under extreme situations, how interstellar voyagers endure, and how they react to the intensity of a sun such as our own. As the comet drew nearer to its closest approach to the sun, a rising sense of expectation spread throughout the community. For the critical period surrounding Atlas's closest approach to the sun, astronomers meticulously planned for continuous monitoring. Their preparations encompassed a spectrum of potential outcomes, ranging from the catastrophic to the merely anomalous. They braced for the possibility of fragmentation, sudden violent outbursts of material, or even total disintegration under the intense solar assault. Yet, despite constructing their most pessimistic predictive models, these scientific forecasts proved utterly incapable of anticipating the subtle, graceful phenomenon actually occurring. Atlas was not succumbing to chaos. Instead, it appeared to be engaged in a form of cosmic choreography. A set of governing principles, only faintly discernible to human understanding, seemed to dictate its behavior. Its trajectory offered conclusive evidence of an origin lying far beyond the familiar boundaries of our own solar system. Unlike the vast majority of comets, which are gravitationally bound to orbit the Sun in predictable ellipses, Atlas followed a distinctly hyperbolic path. Its velocity was demonstrably too great to be captured by the Sun's gravitational pull, confirming its status as an interloper.
This object had entered our solar neighborhood uninvited and unbound, a genuine relic adrift from another star system. It carried with it not only tangible matter, dust, ice, and rock, but also an encoded history preserved within its frozen depths and radiation-scarred exterior. Every instrument reading, every spectroscopic analysis reinforced this profound realization. Atlas was not simply passing through, it was delivering a tangible message written in cosmic ink, a communication from the vast and unknown regions beyond our solar neighborhood. As the final days leading up to perihelion intensified the sense of anticipation, the mystery reached an almost fevered pitch. The comet's unexpected brilliance, its elongated and irregular form, the peculiar patterns of its emissions, all these distinct characteristics converged on a single, undeniable conclusion. The universe was revealing something truly extraordinary. Here stood an object, a silent witness to eons of isolation, having endured the relentless barrage of cosmic radiation and traversed unimaginable distances through the cold void of interstellar space. The stage was set for an unparalleled cosmic response. Observatories, both terrestrial and those orbiting high above the Earth, stood poised and vigilant, anticipating the unfolding drama. A profound awareness permeated the scientific community.
The imminent encounter with the interstellar traveler promised not merely to illuminate our understanding of comets or the nature of wandering solar system rocks, but potentially to challenge fundamental concepts regarding matter itself. The moment arrived, and as astronomers monitored their instruments and data streams flowed, a singular, undeniable reality crystallized. This object, designated 3I Atlas, transcended the status of a mere scientific curiosity. It had become a profound cosmic enigma, a celestial puzzle hurled across the vast expanse of the galaxy directly into our solar system. The arduous quest to decipher its secrets had commenced, its early stages only just revealed. Then the unforeseen occurred, a singular astronomical event destined for decades of rigorous scrutiny, analysis, and heated debate. As 3I Atlas reached its closest approach to our Sun on the 29th day of October in the year 2025, the global astronomical community witnessed an occurrence utterly alien to existing knowledge. A sudden, explosive surge in brilliance erupted from the comet, directly contradicting every theoretical model, every computational forecast, and every established assumption regarding the typical behavior of cometary bodies venturing into the inner solar system. Years of meticulous tracking had already revealed a steady climb in the object's luminosity as it journeyed inward, revealing its bizarre three-part structure and subtle rhythmic variations in its emitted light.
Yet, these careful observations conducted over several weeks offered no conceivable harbinger for the sheer intensity that would immediately follow its perihelion passage. Within hours, Atlas's brilliance surged to levels reminiscent of an astronomical fireworks display. Data meticulously gathered by ground-based observatories, already analyzing the comet's changing light curve with great precision, confirmed an increase in brightness that nearly doubled the highest predictions made for its anticipated proximity to the Sun. Advanced space-based observational platforms definitively verified the extraordinary astronomical event. Specifically, the SOHO spacecraft's highly specialized coronagraphs, constructed explicitly for scrutinizing celestial bodies in the Sun's immediate vicinity, captured sequential imagery documenting an abrupt and intense radiative outburst within the comet's coma. The phenomenon bore a striking resemblance to the legendary figure Atlas engulfed in sudden internal combustion, releasing energy at a scale vastly exceeding that of any previously recorded cometary activity within our solar system. A team of astronomers rapidly initiated intensive analysis to unravel the physical processes driving this unexpected luminous surge. Conventional cometary behavior models predict a gradual process where volatile substances, primarily water ice and carbon dioxide, sublimate as the comet nears the Sun, leading to a predictable increase in brightness and material ejection. Atlas, however, fundamentally defied these established principles. The catastrophic outburst manifested without any preceding warning signs, and its sheer magnitude was entirely unprecedented in observational history. Swift calculations by the observing team estimated the prodigious quantity of material expelled from the comet. Initial assessments indicated that Atlas was ejecting multiple tens of times more water molecules than would be typical for a comet at this specific phase of its solar approach. The figures were profoundly staggering. While an ordinary comet would require weeks or even months to release such a volume of material, Atlas accomplished this expulsion within the span of merely hours. Early spectral diagnostics provided the first crucial clues regarding the underlying mechanism. Sophisticated instruments capable of capturing light across ultraviolet, visible, and near-infrared wavelengths revealed that the comet was undergoing a dramatic transformation beyond mere brightening. Its coma was shifting in coloration. The emitted light displayed a distinctly blue hue, a highly unusual spectral signature for comets situated close to the solar body. Initial interpretations of the spectral data pointed towards the potential presence of complex molecular compounds, specifically carbon-based chains, such as C2, alongside nitrogen-containing molecules like amidogen, NH2, explaining this anomalous chromatic shift.
The observed phenomena, while not inherently rare in occurrence, defied previous records through the extraordinary intensity and velocity of their release. Scientists theorized that the comet's unique behavior stemmed from its internal chemistry being abruptly exposed, likely precipitated by the catastrophic failure of a protective crust which had previously shielded its volatile core throughout its immense journey across the star-studded expanse between solar systems. The combined data from numerous sophisticated instruments constructed a complex, though initially bewildering, portrait of the event. The GO-9 instrument, originally designed for vigilant solar monitoring, recorded dramatic fluctuations in light intensity. These rapid spikes suggested numerous, localized eruptions, erupting almost simultaneously across the comet's pockmarked surface. Simultaneously, the STEREOA instrument provided invaluable stereoscopic imagery, revealing the intricate three-dimensional structure of the violent outburst. The comet's nucleus, already possessing a distinctly irregular and lumpy form, became the epicenter of multiple furious activity zones emerging concurrently. This unleashed a diffuse, elongated radiant glow, a stark contrast to the sharp, well-defined coma typically surrounding ordinary comets. Essentially, the celestial body known as Atlas appeared to be undergoing a cataclysmic eruption spanning its entire length, presenting astronomers with a coordinated and unprecedented display of activity, a phenomenon unseen in the recorded history of astronomical observation. Reactions among the scientific community ranged from profound astonishment to a cautiously ignited excitement bordering on disbelief. Dr. Carl Baton, monitoring the event from the U.S. Naval Research Laboratory, described the occurrence as a fundamental revision of established understanding, declaring it a complete rewrite of our expectations regarding comet behavior. Dr. Chi-Chang Jiang, observing through the Lee Observatory, termed the outburst utterly extraordinary, emphasizing that such a singular event forces a re-examination of assumptions held for decades. In response to this sudden celestial spectacle, observatories scattered across the globe swiftly recalibrated their instruments, adjusted observation schedules, and initiated real-time data sharing to capture every detail of this extraordinary phenomenon.
This proposed that a substantial reservoir of volatile ices lay hidden beneath a robust protective crust, potentially composed of carbon dioxide or other radiation-resistant materials. As the comet drew perilously close to the sun's intense heat, this shielding layer catastrophically failed. Suddenly, the trapped volatile substances were exposed to the relentless solar radiation, triggering a violent process of sublimation. This explosive transformation of solid directly into gas released enormous quantities of material, causing a dramatic surge in the comet's luminosity. Nevertheless, even this sophisticated explanation failed to resolve all the mysteries surrounding Atlas. Detailed spectral analysis revealed that specific elements were being ejected at velocities exceeding what standard physics predicted for the sublimation of typical ices. Furthermore, astronomers noted a subtle but distinct shift in the comet's rotation following the intense outburst, strongly suggesting that the mass ejection had been uneven and strongly directional. For those accustomed to the relatively predictable behavior of comets, these observed anomalies were profoundly significant. They pointed towards an internal architecture far more intricate than the common perception of a simple amalgamation of ice and rock. This complexity likely stemmed from billions of years spent traversing the harsh conditions of interstellar space, enduring relentless bombardment by radiation, cosmic rays, and environments that no comet normally found within a solar system could possibly experience. As Atlas's brilliance reached a level detectable by amateur astronomers using modest telescopes, visual magnitude 9 becoming readily visible, reports of sightings began to proliferate, adding a human dimension to the scientific fascination. Though barely discernible to the unaided eye, the comet Atlas revealed its presence clearly to those equipped with telescopes and aware of its precise celestial coordinates. A wave of global interest surged through the astronomical community, visible in online discussions and specialized forums, as enthusiasts and professionals shared images and live reports, creating a shared moment of wonder directed at an interstellar traveler. However, despite this widespread attention and the valuable contributions from dedicated observers, the gathered information remained incomplete and pieced together. Truly continuous and distortion-free monitoring of the comet's dramatic perihelion outburst demanded the unparalleled clarity of space-based observatories, instruments whose limited observation time was fiercely contested by numerous research teams. Complementing these efforts, radio telescopes provided crucial additional data, suggesting that Atlas was shedding water vapor at rates significantly exceeding initial predictions.
Detailed measurements indicated that in the critical days preceding its closest approach to the Sun, the comet was ejecting approximately 5.7 times 10 to the 28th power molecules of water every second. This staggering quantity equated to tens of thousands of tons of material being expelled each and every second. To contextualize this immense activity, a typical comet of Atlas's dimensions might release only a tiny fraction of this volume over the course of an entire month. The sheer scale of the outburst was breathtaking, evoking vivid comparisons to a colossal cosmic fire hose suddenly turned fully on. Astronomers were not merely gathering data, they were actively witnessing a fundamental transformation unfolding in real time. Every new measurement pointed to Atlas's surface and subsurface structures being actively reshaped. The comet displayed an elongated luminous glow, lacked a pronounced dust tail typically seen in such bodies, and exhibited gas emissions with distinct directionality. All these observations hinted at powerful and previously unfamiliar processes actively at work within the comet itself. Scientific minds turned their intense focus to a profound possibility. The very heart of the comet might harbor untouched material originating from its distant home star system. This primordial substance, seemingly preserved within, had been locked away for eons behind an outer shell formed from ice subjected to relentless stellar radiation and subsequently hardened. If this hypothesis proved correct, the dramatic explosion observed during the close approach to the Sun represented an unprecedented and invaluable glimpse into the unaltered interior of an object traversing the void between stars, a specimen whose formation spanned billions of years. The human reaction to this cosmic revelation mirrored the sheer scientific wonder being generated. Across the world, inside the hushed confines of observatories, researchers held their breath. They meticulously monitored streams of real-time telemetry data and scrutinized live imagery captured from powerful telescopes. Communication lines buzzed non-stop as dedicated teams exchanged interpretations, debated emerging theories, and sought consensus. Within mere hours, virtual conferences sprang into action, assembling leading specialists from diverse fields. These experts immediately began weighing the profound potential implications of the event, analyzing its significance through every possible lens. While news outlets, ever receptive to dramatic celestial spectacles, quickly amplified the story for a broad audience, it was the dedicated scientific community that truly grasped the immense weight of the moment. They were actively witnessing the unexpected and highly dynamic behavior of a genuine visitor from another stellar neighborhood.
The significance of this observation extended far beyond the spectacular outburst itself. It resonated with the potential to reshape fundamental understanding. By the time the perihelion period concluded, marking the comet's closest approach to the Sun, it became unequivocally clear that this single object, designated 3IA Atlas, had fundamentally rewritten established paradigms. The nature of its explosive outburst directly challenged every existing model, shattered long-held expectations, and forced a re-examination of all prior assumptions regarding interstellar comets. Detailed observations further suggested that this dramatic event was not an isolated incident, but rather the visible manifestation of a complex, multi-phase process unfolding within the comet. Each distinct phase held the promise of unveiling new and critical insights into the comet's intricate internal structure, its precise composition, and the long and storied history encoded within its frozen depths. The observations gathered during this period would become the cornerstone of extensive research, fundamentally shaping our comprehension of how objects originating from beyond our solar system react when subjected to the immense energy radiating from a neighboring star. Astronomers, contemplating the dramatic outburst, highlighted its most profound significance. This celestial event transcended mere spectacle. It functioned as an invaluable teacher. Its behavior starkly revealed the constraints of our existing theoretical frameworks, serving as a potent reminder that interstellar space constitutes a formidable and capricious realm capable of birthing entities possessing characteristics utterly foreign to our terrestrial experience. Each surge in luminosity, every spectral deviation observed, every unexpected emission detected, each represented a vital clue, a message originating from a distant world, arriving not in silence, but through the spectacular flare of an outburst. This display left the scientific community simultaneously exhilarated by the revelation and perplexed by the complexities it presented. Consequently, as Oumuamua receded from the Sun's vicinity, departing, with a trail of unprecedented data and unresolved questions, the feeling of awe and inquisitiveness intensified. The perihelion outburst marked no termination. It signaled a commencement, a demonstration of the comet's extraordinary nature and a poignant reminder that the universe is profoundly stranger than our current models permit us to envision. Scientists would meticulously analyze every observation, simulate every anomaly encountered, and fervently debate every theoretical possibility. Yet, one undeniable truth persisted. Oumuamua had indelibly inscribed its presence, and the narrative of this interstellar visitor was only just beginning.
As the dust settled following the dramatic perihelion outburst, astronomers shifted their focus towards a more subtle yet equally astonishing phenomenon. The remarkable blue luminescence radiating from Comet Atlas captured astronomers' attention with its striking departure from the usual pallid white or faintly yellowish glow emitted by most comets. This distinct blue tint was not merely a fleeting anomaly, but a consistent and quantifiable shift toward the shorter wavelengths of light, detectable through both ground-based telescopes and spaceborne observatories. Such a spectral transformation signaled profound molecular activity occurring within the comet, revealing previously obscured processes triggered by its perihelion, the closest approach to the Sun. The breakthrough emerged from high-resolution spectrographs aboard the James Webb Space Telescope, collaborating with specialized instruments aboard the Solar and Heliospheric Observatory and the 9th satellite in the Geostationary Operational Environment Satellite Series, GOES-9. These advanced tools, capable of dissecting light across ultraviolet, visible, and near-infrared wavelengths, uncovered an unexpected dominance of specific molecular signatures within the comet's emissions. Among these, two stood out: diatomic carbon, C2, and imidazine, NH2, both familiar components in cometary atmospheres produced as frozen ices sublimate under solar feeding. Yet, in Atlas's case, the intensity, timing, and proportional ratios of these molecules defied prior observations. Diatomic carbon, a highly reactive molecule typically generated when organic compounds in the comet's nucleus decompose under solar radiation, appeared with unprecedented vigor. Meanwhile, imidazine, a radical-bearing nitrogen, offered tantalizing clues about the comet's chemical heritage, suggesting complex pre-solar system chemistry preserved within its icy depths. The interplay of these molecules, observed with unprecedented clarity, painted a vivid picture of a celestial body undergoing dramatic transformation as it neared the Sun, reshaping our understanding of cometary composition and evolution.
Spectrographic analysis recorded emission rates significantly surpassing predictions derived from standard sublimation models. This pointed to a dramatic event. A vast reservoir of chemically intricate material, long shielded deep beneath the comet's protective surface layers, had suddenly been unleashed by the Sun's intense energy. This luminous effect transcended mere visual spectacle. It served as a tangible indicator of profound internal activity. The blue light was, in essence, a visual fingerprint, revealing processes that had quietly unfolded over billions of years within the cold, dark interstellar medium. Scientists swiftly grasped that the blue glow was narrating a much deeper cosmic history. In the comets of our familiar solar system, the interplay between solar radiation, surface heating, and the resulting release of gases follows a relatively predictable sequence. Atlas, however, defied this established pattern. Its behavior was anomalous. Certain zones on the comet's surface demonstrated a markedly accelerated rate of gas release, while adjacent regions appeared comparatively dormant, contributing little to the overall outgassing. This uneven activity suggested a complex internal structure or composition, hinting at the diverse and ancient processes that had shaped its core long before it journeyed into our neighborhood.
This unexpected blue emission forced scientists to reconsider long-held assumptions regarding molecular survival within the harsh conditions of interstellar space. For an object like Atlas, which had journeyed for billions of years through the vast emptiness of cosmic voids, prolonged exposure to pervasive galactic radiation would, according to prevailing theories, have stripped away many of its more fragile molecular compounds. Yet here they were, seemingly intact and highly reactive, actively producing emissions that suggested both remarkable preservation and a sudden, dramatic activation. Some scientific theorists propose that Atlas's outermost layers, having been hardened and chemically altered by cosmic rays during its long voyage, functioned effectively as a protective shield. This shield, they suggest, safeguarded the more delicate molecules residing deeper within the comet's structure, until the intense heat of perihelion triggered their sudden and powerful release. The blue glow emanating from the comet was far more than a mere visual spectacle. It was a chemical time capsule, offering direct evidence of the comet's long and complex journey. This realization had profound implications for the study of comet chemistry, challenging the prevailing view of comets as simple remnants of the early solar system. For decades, comets have been considered as archives of early solar system material, providing crucial clues about the building blocks of planets and life itself. However, the comet Atlas forced scientists to broaden their perspective. This interstellar visitor was not a product of our solar system. It originated around a star whose chemical environment was unknown, whose radiation history was unique, and whose formation conditions could differ dramatically from those that shaped our own comets. The blue glow suggested that interstellar comets could carry entirely new chemistries, ones that challenge our understanding of molecular survival, isotopic ratios, and organic complexity in space. Researchers were quick to investigate the ratios of carbon to nitrogen compounds in Atlas's emissions. Preliminary analyses indicated unusual proportions, unlike those measured in solar system comets. The presence of imidrogen in significant quantities alongside intense C2 emissions pointed to a nucleus rich in complex organic chemistry. While some of these molecules are commonly found in comets, their concentration and release pattern were exceptional. It was a chemical signature that told a story billions of years old, one that hinted at processes far beyond our direct observation until now. The discovery of these unique chemical signatures provided a window into the distant past, offering insights into the processes that shaped the early universe and the potential for life in other parts of the cosmos.
Beyond the intricate chemistry itself, the comet's distinctive blue luminescence held significant practical advantages for astronomical observation. Emitting intensely at shorter, bluer wavelengths, Atlas offered astronomers an exceptionally rare chance to probe the intricate structure and dynamic behavior of a cometary coma. This unique emission characteristic meant the glow originated primarily from gases, drastically reducing the confusing interference typically caused by the vast amounts of dust present around comets. Normally, this pervasive dust obscures crucial molecular emissions, rendering detailed spectroscopic analysis exceedingly challenging. However, in the case of Atlas, the pronounced scarcity of dust alongside the overwhelming dominance of gaseous emissions created a remarkably clear observational window. Researchers could now meticulously map the distribution of specific molecules in near real time, capturing the formation and movement of distinct jets, powerful plumes, and vast, diffuse clouds of gas with unprecedented clarity and precision. Each individual frame captured by telescopes, every spectral measurement taken, contributed another vital piece to the complex puzzle, unveiling a comet that simultaneously resembled familiar comets in its broad outlines while presenting entirely alien features in its intricate details. The comet's ethereal blue radiance also profoundly captured the imagination of the general public. Color-enhanced and contrast-optimized images released by space agencies and observatories depicted a hauntingly beautiful, ghostly blue halo stretching majestically across the vast space enveloping the comet's nucleus. Even individuals lacking any understanding of the underlying chemical processes could intuitively sense the profound strangeness of this celestial object. It evoked the impression that Atlas carried within its core the very colors of a distant, unfamiliar star system, broadcasting them silently across billions of kilometers of empty interstellar space for humanity to witness. In this manner, the comet transcended its status as mere scientific curiosity, transforming into a breathtaking cosmic spectacle. It served as a vivid, tangible reminder that the universe continues to harbor phenomena far beyond our current comprehension and understanding. This remarkable visibility also prompted scientists to begin theorizing that the source of the blue glow might be intricately linked to the comet's internal architecture and composition. The enigmatic nature of Atlas's core, potentially composed of a stratified matrix of frozen volatiles intermingled with radiation-altered compounds, offered a plausible explanation for its dramatic outbursts and chromatic shift. Unlike the gradual, predictable shedding characteristic of typical cometary bodies, Atlas exhibited a distinctly erratic rhythm. Instead of a steady erosion, it seemed prone to sudden, explosive releases of chemically complex gases.
These bursts appeared to be precipitated by internal mechanisms, perhaps intense localized stresses fracturing the structure, thermal shocks causing surface cracks, or the catastrophic collapse of a hardened outer crust. Each successive observation reinforced a compelling conclusion.
Atlas was not a dormant snowball adrift in the void, but a profoundly intricate and dynamically active entity. By the close of November, the scientific community's perspective had fundamentally shifted. Atlas's ethereal blue luminescence ceased to be viewed as a mere peculiarity. It emerged as an intrinsic aspect of its interaction with solar radiation, a defining manifestation of its unique nature. This phenomenon represented a theoretical cometary behavior long speculated about but never before witnessed. It stemmed from a confluence of factors: exceptional chemical preservation within its depths, a highly selective process of outgassing where specific molecules escaped preferentially, and the profound cumulative effects of exposure to cosmic radiation over immense durations. For astronomers, this was nothing short of a paradigm shift. Here stood a comet that had journeyed beyond the conventional boundaries of their understanding, compelling a radical reevaluation of cometary chemistry itself. As Atlas continued its retreat from the point of closest approach to the Sun, the persistent blue glow endured. It diminished gradually, fading like a lingering dream, yet it left an indelible mark on both the sensitive instruments that recorded it and the human imagination that beheld it. This subtle radiance served as a powerful signal that the universe retained mysteries defying our most sophisticated predictions. It was a poignant reminder that visitors traversing the vast interstellar distances could carry within them profound narratives, inscribed not in words, but in the silent language of molecules, the signatures of radiation, and the transformative power of sunlight. For researchers, this celestial discovery served as both an invitation and a reminder to persist in their observations, to delve further into the mysteries of the universe, and to approach the cosmos with humility, given its capacity to generate such astonishing phenomena. The comet, later identified as Comet Atlas, bearing its peculiar radiant blue luminescence, transformed into an unexpected teacher. It illuminated the realization that chemistry in the vastness of space is far from uniform. The comet's journey through interstellar space had left behind traces, marks the humanity is only now striving to decipher. Every comet, every sudden outburst, every subtle shift in its spectral signature offered revelations extending far beyond the boundaries of our immediate cosmic neighborhood.
To astronomers, this luminous comet was more than a celestial object. It was a messenger, a cosmic courier, carrying with it the chemical imprints of a distant star system forever shaped by the relentless passage of time, the sculpting influence of radiation, and the profound solitude of interstellar voids. As scientists meticulously analyzed the deluge of data streaming in from Comet Atlas, one particular observation stood out with undeniable clarity. The staggering volume of water molecules escaping from the comet's surface defied conventional understanding. Through calculations based on both spectroscopic records and observations made by orbiting instruments, researchers determined that Atlas was losing water at rates previously unseen in comets from our own solar system. Between the 2 weeks preceding its closest approach to the Sun, the comet expelled approximately 5.7 times 10 to the 28th water molecules each second. To contextualize this figure, it represented roughly 40 times the evaporation rate recorded just 1 month prior. A revelation so extraordinary that even seasoned experts studying comets for decades were left in awe. This level of water loss was not merely significant, it challenged existing theories and sparked new questions about the behavior of interstellar comets. For a comet exhibiting Atlas's substantial estimated dimensions, the rate of water vapor release reached the staggering magnitude of tens of thousands of tons each second. Achieving this level of ice sublimation demands an immense expenditure of energy, a fact that strongly suggests the presence of complex internal processes and unique material properties within the comet's nucleus. These factors appear to operate beyond the scope of conventional thermal models designed for typical cometary behavior. Standard comets, as they journey closer to the Sun, gradually emit water vapor. This process naturally generates a distinctive tail composed of both reflected sunlight from dust particles and glowing gases, creating the iconic feature that defines these celestial objects. However, Atlas consistently demonstrated an exceptional defiance of established cometary norms. One of the most remarkable and perplexing characteristics observed during this period was the conspicuous lack of any visible dust tail. Such tails are a direct consequence of solar heating, vaporizing surface ices. The escaping gas carries along entrained dust particles which then reflect sunlight, forming the brilliant flowing structures universally associated with comets. Atlas, in stark contrast, profoundly contradicted this expected visual signature. Despite ejecting vast quantities of water vapor and other volatile substances at an extraordinary rate, the comet's tail structure was astonishingly faint or entirely absent in many observations. Instead of the anticipated streaming trails, viewers described a faint, elongated luminous glow surrounding the nucleus.
This glow presented an almost spectral or ghostly appearance, devoid of the distinct, concentrated streams typically observed. This complete absence of a conventional dust tail ignited intense debate and speculation within the astronomical community. Numerous theories emerged to explain this anomaly. A significant hypothesis proposed that the comet's dust content might be inherently lower than that found in most well-studied comets. This deficiency could potentially be explained by prolonged exposure to the harsh environment of interstellar space over billions of years. Continuous bombardment by micrometeorites and relentless exposure to cosmic radiation were thought to have progressively eroded, altered, or even volatilized the dust residing on the comet's outermost layers. This long-term processing might have left the comet's preserved nucleus predominantly composed of volatile ices, with significantly depleted or altered particulate matter available to form a traditional dust tail. Several alternative theories emerged regarding the missing comet tail. Some scientists propose that the dust particles might indeed exist within the comet's environment. However, these particles could be so infinitesimally small or exceptionally thinly scattered throughout space that they failed to aggregate into a discernible, coherent tail. Even advanced astronomical instruments, capable of detecting minute celestial phenomena, would likely be unable to observe such a structure. Another significant line of inquiry focused on the crucial role played by carbon dioxide. Detailed astronomical observations revealed a compelling pattern. Carbon dioxide gas was escaping from the comet long before its dramatic encounter with the Sun. Specifically, this outgassing activity was detected at distances of roughly 3 astronomical units from the Sun, occurring well in advance of the intense perihelion event. This early release of carbon dioxide gas appears to have had a profound cooling effect on the comet's outer layer. Effectively, this escaping gas functioned as a natural insulating barrier overlying the more volatile water ice beneath the surface. By regulating the temperature of this surface layer, the carbon dioxide shield may have significantly slowed down or even prevented the premature sublimation of the underlying water ice. Consequently, this mechanism could help explain the nature of the outburst, why it manifested with such abrupt and cataclysmic force. The theory suggests that the outburst occurred when this protective carbon dioxide layer finally became exhausted or developed cracks and fractures. Once compromised, the pristine water ice lying directly beneath was suddenly exposed to intense solar heating. This exposed ice would then undergo violent sublimation,
transforming rapidly from solid to gas and generating the massive, observable outflow of material witnessed during the event.
If this hypothesis proves accurate, it provides a captivating glimpse into the complex behavior of interstellar comets like Atlas. Unlike comets originating within our own solar system, which typically exhibit predictable patterns of material loss and sublimation as they near the Sun, Atlas may have evolved a unique surface structure. This structure was specifically adapted over billions of years to preserve its most volatile components. The protective carbon dioxide layer can be envisioned as a sophisticated time capsule. It functioned to insulate the comet's interior, maintaining chemical integrity despite enduring the extreme and hostile conditions of the interstellar medium for eons. Therefore, the sudden exposure of the water ice upon the comet's arrival in the inner solar system is not merely an incidental consequence of proximity to the Sun. Instead, it represents a profound revelation, a direct window into the comet's singular evolutionary history and the extraordinary adaptations its surface architecture developed during its long journey through the galaxy.
However, once the object reached a critical proximity to the intense solar heat at perihelion, this protective CO2 shell either fractured or became depleted. This sudden exposure unleashed the pent-up volatile water ice, triggering an explosive and dramatic increase in brightness as vast quantities of water vapor were rapidly ejected into space. The perfect alignment of this specific timing, the detected chemical signature confirming water vapor release, and the structural implications of the delayed activity collectively explained the extraordinary event witnessed by astronomers. Yet this very sequence also suggested that what was observed constituted only a single dramatic stage within a potentially much longer and significantly more complex cycle of activity unfolding over the object's journey. Additional revelations emerged from detailed spectroscopic measurements tracking the outflow of water molecules. These sophisticated techniques allowed scientists to quantify not only the immense volume of water being lost from the nucleus, but also to map its distribution across the entire surface. The resulting data unveiled a surprising pattern. The loss of water vapor was not uniform, but exhibited distinct directional characteristics. Specific regions on the nucleus were observed to be intensely active, releasing staggering amounts of water vapor, while other areas remained remarkably quiet and relatively inert. This stark contrast in activity levels across different surface locations provided crucial insights into the object's dynamic behavior and surface properties during this highly active phase. Astronomers further scrutinized the dynamics of the ejected material, specifically the velocity of the expelled water molecules. Established astronomical models dictate that the speed of these molecules should correlate directly with the temperature of the parent comet surface and the local strength of its gravitational pull. However, measurements from Atlas consistently revealed molecular velocities far exceeding these standard predictions. This critical discrepancy strongly suggested a mechanism far more violent than the slow, steady sublimation process typically associated with cometary activity. Instead, the high speeds pointed towards a sudden, explosive release of material. Building on this observation, some scientific teams proposed a compelling scenario for Atlas's dramatic behavior. They theorized that substantial quantities of water ice might be buried deep beneath the comet's outer crust, a hardened layer composed predominantly of carbon dioxide, CO2. This deeper ice could be held under considerable pressure by the overlying material. The critical moment arrived when this resilient CO2 crust developed a fissure. The rupture would have unleashed this pressurized ice in a dramatic fashion, functioning analogously to a colossal geyser erupting through the surface. This sudden decompression would propel vast clouds of water vapor into the surrounding vacuum of space at exceptionally high velocities. This explosive process, they argued, not only explained the anomalous molecular speeds, but also contributed significantly to the comet's uniquely pronounced elongated coma, its spectacular glowing envelope. The overall picture painted by Atlas was profoundly unusual. An extraordinary rate of water vapor loss combined with the conspicuous absence of the familiar dusty tail typically trailing such celestial wanderers. This combination crafted a portrait of a comet utterly alien compared to those native to our solar system. Atlas seemed to defy conventional expectations, demonstrating an inherent capacity to surprise. It served as a powerful reminder that objects arriving from interstellar space carry complex histories, intricate internal structures, and unique compositions that current astronomical models designed for solar system inhabitants struggle to fully encompass or anticipate. The observations fundamentally challenged long-standing scientific assumptions regarding the mechanisms driving cometary activity, the evolutionary processes governing volatile-rich bodies over immense timescales, and the critical protective role played by surface layers in preserving primordial material across the eons of cosmic time. Even the distribution of the comet's gaseous emissions revealed a profound underlying complexity. Astronomers, meticulously mapping the intensity of water vapor escaping across the celestial body's surface, identified distinct zones exhibiting far greater activity than their surroundings. These hotspots potentially aligned with fractures or regions of an unusually thin crust, acting as conduits for the pressurized interior. This patchwork pattern of outgassing suggested the nucleus had undergone a long and intricate sculpting process over billions of years, shaped by the relentless forces of cosmic weathering. The result was a heterogeneous structure, exhibiting distinct chemical compositions and thermal properties across its surface, a testament to its ancient and dynamic history. The dramatic outburst observed at perihelion, the comet's closest approach to the Sun, was far more than a simple reaction to increased solar heating.
It represented the culmination of immense internal stresses building within the comet's complex architecture. The intense solar energy acted as the trigger, forcing the hidden structural weaknesses and volatile reservoirs to reveal themselves in a spectacular display. The comet's lack of a prominent dust tail also carries significant implications for future observation strategies. Traditionally, comets are discovered and tracked due to their bright reflective tails composed of dust particles, which scatter sunlight effectively. An object like Atlas, which possesses a relatively faint dust tail yet experiences extreme gas outflow, presents a unique detection challenge. If such an interstellar wanderer were to approach the inner solar system from an unfavorable viewing angle, its low dust visibility could allow it to evade detection entirely by conventional telescopes reliant on dust reflections. This realization has sparked important discussions about refining our search and study techniques for interstellar objects, emphasizing the critical need for instruments sensitive to detecting gas emissions alongside traditional dust-based observations. In this context, Atlas has served a dual purpose. It has significantly expanded our understanding of cometary chemistry and internal processes, while simultaneously highlighting critical gaps in our current observational methodologies. The staggering volume of water lost by Atlas, the unexpected absence of a substantial dust tail, and the crucial role played by the protective carbon dioxide layer all converge to narrate a compelling story.
This story speaks of an object meticulously shaped over billions of years within the cold, dark depths of interstellar space, its structure and composition reflecting a long, complex journey through the cosmos. The celestial traveler known as Atlas carried within it a remarkable preservation mechanism. Its most volatile constituents were carefully shielded by an outer stratum composed primarily of carbon dioxide. This protective layer remained intact until the comet drew perilously close to the Sun. Only then, subjected to the intense solar heat, did this CO2 shield trigger a sudden, violent release. The result was a breathtaking spectacle, a dramatic interplay of light, complex chemistry, and fundamental physics. This extraordinary event directly challenged established notions about cometary behavior and provided humanity with an unparalleled window into the hidden depths of an interstellar visitor. Consequently, as the comet continued its outward trajectory following its closest approach to the Sun, astronomers were left with a treasure trove of data and a multitude of profound questions. The sheer magnitude of the water molecule outflow generated by Atlas, measured in tens of thousands of tons every single second, presented a significant scientific puzzle demanding extensive investigation.
Researchers embarked on a complex quest to unravel the intricate pressures, extreme temperatures, and unique structural features within the comet that could possibly explain such exceptionally violent behavior. Furthermore, the conspicuous and complete absence of a traditional dust tail forced a fundamental reconsideration of how humanity defines and classifies comets, particularly those originating from beyond the boundaries of our own solar system. The critical role played by the seemingly minor carbon dioxide layer served as a powerful reminder that even subtle, easily overlooked characteristics can exert a profound influence on the evolutionary path and observable manifestations of celestial bodies traversing the cosmos. Through its astonishing actions, shedding tens of thousands of tons of water every second, while paradoxically leaving its tail conspicuously absent, Atlas had once more powerfully demonstrated that objects arriving from interstellar space are not merely curious scientific novelties. They stand as genuine messengers, emissaries hailing from distant worlds. These cosmic envoys bear invaluable lessons concerning the nature of chemistry, the laws of physics, and the immense diversity of planetary systems scattered throughout the galaxy. To truly comprehend the story of Atlas, one must inevitably contemplate the vast and ancient journey it has undertaken across the cold, star-strewn expanse of interstellar space. A journey stretching over billions of years, traversing the immense voids between stars, through environments that defy imagination. In this vast expanse, the comet has not remained passive. It has been continually subjected to intense bombardment by galactic cosmic rays, high-energy particles, predominantly protons, that permeate the Milky Way galaxy. Unlike solar radiation, which primarily influences objects within a star system, cosmic rays operate over astronomical distances, penetrating deep into the nuclei of comets and altering their chemical and physical structures over unimaginable timescales. Infrared observations, particularly those obtained by the James Webb Space Telescope, have provided unprecedented insight into the effects of this cosmic bombardment. The Webb's near-infrared spectrograph can detect the subtle signatures of radiation-processed materials, revealing features that are invisible to visible light telescopes. In the case of Comet Atlas, the Webb detected a surface that is remarkably different from any comet previously studied. The infrared spectra show a hardened, irradiated crust extending tens of feet into the nucleus of the comet, with chemical markers indicating prolonged exposure to high-energy particles. This irradiated crust is not merely a superficial layer. Computer simulations suggest that galactic cosmic rays have penetrated as much as 50 to 65 feet into the surface, creating a dense shell of altered material.
The composition is intricate, consisting of chemically transformed ices, amorphous carbon compounds, and radiation-altered organics. This outermost stratum bears little resemblance to the original primordial blend of ice and dust that first coalesced around Atlas's native stellar nursery. Instead, it functions as a tangible chronicle of its remarkable odyssey, intrinsically forged from the very fabric of the interstellar medium traversed. The presence of this distinct crust carries significant ramifications, not only elucidating the dramatic outburst witnessed during its solar approach, but also reshaping our fundamental comprehension of interstellar comets. A direct consequence of this transformation is that the hardened exterior of Atlas no longer exhibits the expected physical behavior of typical cometary ice. Established models for comet sublimation generally presuppose relatively uncomplicated surface compositions, where solar radiation incrementally vaporizes surface ices in a largely predictable and orderly fashion. However, the irradiated crust enveloping Atlas has undergone profound hardening and chemical alteration, creating an effective insulating barrier that shields the interior. This protective layer substantially impedes the conventional process of sublimation. Only when this resilient shell sustains fractures or undergoes significant erosion does the latent interior unleash the prodigious quantities of water vapor and gaseous compounds responsible for the spectacular perihelion outburst observed by astronomers. Astronomers further recognize that this pervasive crust introduces substantial complexity into the scientific endeavor of deciphering the comet's true composition. Sole reliance on surface-level measurements risks presenting only a distorted view. The observed characteristics may primarily reflect the cumulative effects of billions of years of relentless cosmic processing and transformation endured during its interstellar voyage, rather than offering a direct glimpse into the pristine, unaltered materials originating from its stellar birthplace. In essence, Atlas's outer shell constitutes a direct product of its arduous journey through space, not a faithful representation of the chemistry inherent to the star system from which it initially emerged. Concealed beneath this irradiated, hardened exterior, however, likely persists untouched reservoirs of ancient ices and complex compounds. These buried remnants potentially preserve the chemical signature of an entirely unobserved planetary system, a silent testament to the origins Atlas left behind long ago. The stark contrast between the heavily processed outer shell and the potential untouched interior of the comet introduces a compelling layer of mystery. This enigma has ignited profound excitement among scientists and fueled an intense drive to investigate deeper into its secrets.
Infrared observations provided crucial insights, revealing that the irradiation history wasn't consistent across the surface. Certain sections of the crust exhibited greater density, marked by stronger spectral signatures pointing to elevated levels of radiation-altered materials. Conversely, other areas appeared noticeably thinner or contained fractures and weaknesses. This inherent unevenness in the crust likely accounts for the observed directionality of gas and water vapor escaping during the comet's closest approach to the Sun. The jets weren't emitted uniformly. Instead, they erupted specifically from these vulnerable points within the irradiated crust. These eruptions manifested as localized flares, actively contributing to the comet's distinctive, elongated, ghostly luminous envelope. Every plume and surge of brightness observed was intrinsically linked to the intricate internal architecture, a structure meticulously sculpted over billions of years. The chemical transformations induced by radiation extend beyond mere physical restructuring.
Cosmic rays possess the remarkable capability to disassemble simple molecular building blocks, subsequently reassembling atoms into more complex compounds and even generating entirely novel chemical species that would not naturally form under terrestrial conditions. For the comet known as Atlas, these cosmic ray-driven reactions may offer a plausible explanation for the detected abundance of specific molecules such as diatomic carbon and amidogen, which contribute to the characteristic blue-hued glow. These reactive radicals could very well be the direct products of such high-energy cosmic ray interactions occurring within the outer layers, released explosively during the heightened activity at perihelion. This phenomenon serves as a powerful reminder that interstellar space is far from empty. It functions as a dynamic laboratory of high-energy physics, continuously shaping comets in ways that profoundly challenge and expand our terrestrial understanding of chemistry and planetary science. The revelation concerning the age of Atlas's irradiated crust fundamentally underscores the staggering scale of its galactic odyssey. This celestial object is not merely a comet that has traversed a relatively brief interplanetary journey. Rather, it represents a traveler whose existence may span the profound majority of cosmic history itself, drifting silently and unseen through the vast interstellar void between star systems. This immense timescale carries profound implications, indicating that its surface has endured relentless bombardment by cosmic radiation for billions upon billions of years, a cumulative dose utterly unimaginable for any comet confined within the relative shelter of a planetary system. The relentless exposure to cosmic rays and ultraviolet radiation has fundamentally altered the comet's surface structure over eons.
These cumulative effects have progressively transformed its mechanical properties, subtly modifying its strength and fragility, have chemically modified its composition, breaking down familiar compounds and potentially forging entirely new ones unknown in our local environment, and have altered its thermal conductivity, changing how heat moves through its outermost layers. Consequently, the crust has evolved into a robust, hardened shell. This shell serves a dual purpose. It acts as a protective barrier, preserving the ancient, unaltered material deep within from further external degradation, while simultaneously undergoing profound metamorphosis itself. The outermost regions have been so intensely altered by radiation that they bear little resemblance to the pristine ices and dust typical of comets originating within our own solar system, appearing almost alien in their composition and structure. Understanding this irradiated shell also sparks compelling scientific inquiry regarding the survival of complex interstellar molecules. The outburst observed near its closest approach to the Sun may have released compounds that were uniquely shielded for billions of years, preserved intact beneath this protective crust, only to be liberated when solar heating finally breached the hardened layer. Simultaneously, the intense radiation environment itself could have driven exotic chemical reactions within the crust, generating molecular species entirely characteristic of interstellar space and never before witnessed so clearly in such detail. For researchers, Atlas presents a truly unprecedented laboratory, offering a rare glimpse into both the remarkable preservation of primordial materials and the profound transformative power of cosmic radiation, operating over unimaginable timescales. This provides a crucial bridge between the realms of chemistry, physics, and astronomy, a perspective rarely accessible through the study of objects solely within our own solar system. The very concept of such an ancient, heavily irradiated crust fundamentally reshapes expectations for anticipating and interpreting the characteristics of future cometary visitors originating from beyond our stellar neighborhood.
Comet Atlas's unique characteristics suggest that similar objects entering from interstellar space may possess a complex, layered history of cosmic radiation exposure. This pervasive radiation acts as a transformative agent, effectively obscuring the comet's original, pristine interior materials. Consequently, determining the fundamental composition of these distant visitors becomes an intricate scientific challenge, demanding careful disentanglement of ancient material from that altered during the comet's lengthy passage across the galaxy. The surface of Atlas, in essence, functions as a cosmic palimpsest. Each distinct stratum represents a chapter in an extraordinary narrative written over eons by relentless bombardment from galactic cosmic rays.
These overlapping layers chronicle the comet's arduous journey through the vast, hostile environment of interstellar space. Furthermore, the intense radiation exposure likely induces significant changes to the physical characteristics of the comet's central body, or nucleus. The process can render the outer shell unnaturally hard and brittle, making it susceptible to fracturing under the extreme thermal stresses experienced near the Sun. This altered mechanical state provides a crucial clue to understanding the comet's dramatic explosive activity observed at its closest approach to the Sun. The powerful outbursts may not have stemmed solely from the volatile release of trapped water ice. The fracturing of this radiation-hardened crust, weakened by cosmic exposure, could have played a vital facilitating role. The combination of high pressures building within the nucleus and rapid heating would have exploited these pre-existing weak points. Failures in the brittle crust would trigger jets of escaping gas, initiating a self-reinforcing cycle where the release of material amplified both the mechanical disruption and the chemical reactions occurring on the surface. Every recorded eruption of Atlas thus stands as a direct manifestation of the complex interplay between its internal structure, profoundly shaped by radiation history, and the energetic processes unleashed by solar proximity. The ongoing investigation into Atlas's irradiated outer layer continues to yield new insights as the comet moves further away from the Sun. Each subsequent infrared measurement, every detailed spectral analysis refines and deepens our comprehension of how interstellar comets fundamentally evolve and transform over the immense timescales traversed before reaching our solar system. This irradiated crust is far more than a mere surface curiosity. It is a critical archive holding the keys to understanding these enigmatic cosmic travelers and their journeys across the stars. It stands as a unique chronicle etched across cosmic time, a tangible archive of processes fundamentally impossible to replicate within terrestrial laboratories. This ancient outer layer, forged over eons, and dramatically unveiled during brief, intense encounters with the Sun, encapsulates the comet's essence. Astronomers recognize this crust as serving a dual purpose. It acts as a vital protective shield while simultaneously functioning as a cosmic storyteller. This shield prevents the comet's volatile internal ices from sublimating prematurely into the void, safeguarding materials that would otherwise be irrevocably lost to space. Simultaneously, it meticulously preserves a record of Atlas's extraordinary odyssey, inscribing the cumulative impacts of relentless cosmic rays, pervasive interstellar radiation, and the inexorable passage of time itself. By meticulously examining this irradiated stratum, our scientific inquiry transcends simple observation.
We are, in fact, tracing the immensely long and arduous journey of an object whose travels have surpassed those of any comet known within our solar system. This irradiated crust, therefore, serves as both an essential barrier preserving ancient secrets and a profound revelation, challenging our existing models of cometary evolution. Its properties provide a compelling explanation for the unusual timing of the perihelion outburst witnessed during this close solar approach. Furthermore, it unequivocally demonstrates that interstellar objects like Atlas cannot be considered mere analogues of typical solar system comets. Their unique history and transformation set them apart. Atlas's transformed surface, a direct consequence of billions of years of bombardment by cosmic rays, offers a powerful reminder. It underscores the dynamic, ever-changing nature of the universe, revealing how extreme conditions are required to expose the transformative power shaping matter across the cosmos. As scientists continue their analysis of the gathered data, this cross raises compelling new questions. How profoundly does this radiation-induced process extend beneath the comet's surface, penetrating into the nucleus? What specific chemical transformations dominate at these hidden depths? And most crucially, what profound mysteries and materials await discovery beneath this resilient ancient shield?
It has already explained previously puzzling anomalies, raised compelling new questions demanding further investigation, and serves as a vivid, tangible reminder that interstellar objects carry the distinct and lasting imprint of their journeys. This imprint manifests in ways that are both subtly intricate and profoundly significant. Whether revealed in the distinctive blue glow observed during its closest approach to the Sun, in the staggering outflow of water vapor detected, or in the notable absence of a typical dust tail, the irradiated crust emerges as a unifying and defining feature. It intricately links the domains of chemistry, the principles of physics, and the object's own long interstellar history in a manner that directly challenges and transcends every prior expectation humanity held regarding comets originating beyond our own solar system.
Such a specimen would possess a heritage forged in an environment governed by a distinct stellar composition, a unique blend of elemental constituents shaped by a different radiation history and following an evolutionary path entirely distinct from the one our own solar system experienced. The potential insights into the diversity of planetary formation across the galaxy are immense. The opportunity to examine this extraterrestrial specimen, even from a distance, represents a scientific breakthrough of extraordinary significance. It presents an unparalleled chance to evaluate theories surrounding planetary genesis, stellar composition, and interstellar navigation, concepts that up until now existed solely within theoretical frameworks and computational simulations. Nevertheless, the comet's eons-long odyssey has left its mark, complicating the scientific inquiry. Over billions of years, its surface has undergone relentless transformation. Intense bombardment by cosmic rays has permeated its structure, while repeated thermal fluctuations caused by proximity to stars during its wanderings have induced fragmentation and weathering. Additionally, countless collisions with interstellar dust particles have scarred or subtly altered its exterior. This complex history renders the interpretation of its current composition an intricate process, akin to deciphering a layered historical record. Scientists face the formidable challenge of distinguishing between characteristics that originated during the comet's formation and those that resulted from its prolonged exposure to cosmic hazards. Advanced infrared observations and precise spectroscopic analyses offer promising clues. While the outer strata unmistakably display the effects of radiation-induced chemical changes, the deeper interior may retain a more untouched state. Researchers theorize that protected within its hardened shell lie concealed reservoirs of frozen water, primordial gases, and complex organic molecules shielded from external influences for eons.
If accessible, these materials could provide invaluable insights into the elemental and isotopic composition of the comet's native stellar system. Such comparative studies might illuminate whether other star systems generate identical chemical foundations for life as we understand it, addressing one of humanity's most profound questions regarding our place in the cosmos. The elemental composition of hydrogen, carbon, nitrogen, and oxygen, the fundamental building blocks of life as we know it, presents a persistent question. Do these ratios mirror those found in our own solar neighborhood throughout the vast expanse of our galaxy? The very prospect of encountering truly pristine material, untouched by the processes endemic to planetary systems, ignites profound scientific curiosity. Specifically, it prompts vital inquiries regarding the distinct evolutionary pressures acting upon comets originating from beyond our solar system.
Within our local cosmic environment, comets undergo a relentless sequence of transformations, repeated cycles of intense heating during close approaches to the central star, followed by profound cooling in the frigid outer regions. Intricate gravitational dances and interactions with massive planets that can alter their orbits dramatically, and constant perturbations from celestial bodies. Atlas, the interstellar visitor, stands in stark contrast. For unimaginable epochs, this comet has silently traversed the profound darkness of the interstellar medium, largely shielded from the repeated processing and disruptive encounters that shape comets bound to star systems. However, this isolation came at a cost. Atlas has been subjected to the unyielding assault of cosmic radiation for eons. This uniquely solitary and hostile journey suggests its internal structure might preserve remarkable chemical complexity. This complexity could manifest in ways that are exceedingly rare or entirely absent in the comets originating from our own solar system. Comets whose histories are deeply entwined with planetary influences. In essence, Atlas offers humanity a singular natural experiment. It acts as a probe, investigating chemistry that has evolved in complete isolation, yet under the constant, high-energy bombardment of cosmic radiation, revealing a fundamentally different path of cosmic chemical evolution. Some researchers have ventured even further, postulating the tantalizing possibility of encountering truly exotic compounds within Atlas's depths. Could this comet harbor materials forged under pressures, temperatures, or radiation conditions that simply cannot be replicated within our own solar system? Could it contain amino acid precursors, intricate hydrocarbons, or other crucial prebiotic molecules, all securely locked within its core? These complex molecules might be remarkably well preserved, shielded from the erosive effects of the space environment by a protective crust that has itself been heavily modified by radiation. These are not idle musings or mere speculation. Each significant discovery of complex organic compounds within comets originating from our solar system has fundamentally reshaped scientific understanding, forcing a reevaluation of prebiotic chemistry and the very potential for life elsewhere in the universe. Atlas, therefore, holds the extraordinary promise of extending this vital knowledge to a completely alien stellar environment. It would offer the first empirical comparison of interstellar organic chemistry, providing a crucial benchmark against which the chemical processes occurring within our own solar system can be measured and understood. While the comet's journey has fundamentally altered its outer layers, this very transformation has also unexpectedly amplified our capacity to observe crucial internal processes.
The fracturing of the irradiated crust, followed by dramatic outgassing events during the perilous passage near the Sun, provided an unprecedented indirect window into the comet's hidden activity. The sudden, forceful release of gases, accompanied by distinct spectral signatures and occurring at specific moments, strongly indicates that the comet's nucleus is not uniform. Instead, it exhibits significant heterogeneity, featuring variations in both composition and structure that likely echo the diverse environments from which it originated.
In effect, the comet's dynamic behavior itself functions as a natural probe, continuously unveiling real-time clues about its interior makeup. Astronomers are also beginning to explore profound implications for how planetary systems form. By meticulously comparing isotopic ratios found in the water and organic molecules within the comet's coma to those measured in comets from our own solar system, scientists may gain invaluable insights into whether certain fundamental chemical processes are universal across the galaxy. Are the essential ingredients for forming water-rich planets or even prebiotic chemistry commonplace throughout the cosmos? Alternatively, does this particular system represent a scenario with distinctly unique chemical evolution compared to our own? Each piece of data gathered brings us incrementally closer to resolving these fundamental cosmic questions, progressively extending our understanding beyond the familiar boundaries of our own sun and planets. Yet woven into these remarkable observations is an inherent sense of humility. We cannot physically collect samples from the distant comet Atlas. Our understanding relies entirely on interpreting the light, radiation, and escaped molecules that reach us. These vital signals traverse immense distances, becoming filtered through the comet's own processed radiation crust, altered by the intense heat of the sun, and further modified by complex interstellar processes along their journey. This chain of transformation means we are always interpreting the comet's story through an imperfect lens, a fundamental constraint that underscores the ingenuity required to glean knowledge from the distant cosmos. Each measurement, consequently, represents an amalgamation of undisturbed material and change, a multifaceted narrative demanding meticulous analysis. Researchers are tasked with unraveling these strands, discerning the reverberations from billions of years traversing the cosmos from the initial chemical outline of the comet's origin star system. The potential presence of undisturbed material carries philosophical significance. In a way, Atlas serves as a remnant of another world brought to our threshold, providing tangible proof that solar systems beyond our own are not just theoretical concepts, they are real entities, capable of sending fragments of themselves through the galaxy.
The comet transcends being merely an object for examination. It becomes a conduit between stellar systems, a courier that has persevered through the emptiness to deliver messages across astronomical distances. Its core, concealed beneath the irradiated strata, might harbor the closest approximation we will ever encounter to the foundational material of a far-off star's planetary nursery. However, despite this potential, there is much that remains elusive. The precise makeup of the core, to what extent it maintains its undisturbed state, and the entirety of chemical intricacy are inquiries that may persist partially unresolved for many years. Missions designed to intercept and sample interstellar comets are theoretically feasible, yet extraordinarily demanding. For the present, we depend on the faint hints encoded in the light emitted from Atlas's outgassing, employing advanced models to reconstruct a chronicle etched over billions of years. The astronomical world holds its breath in anticipation. Every fresh glimpse captured by the Webb Space Telescope, the Solar and Heliospheric Observatory, or terrestrial observatories enriches a burgeoning scientific saga. This comet, designated Atlas, presents a fascinating paradox. Its fundamental structure echoes familiar cometary forms, yet its chemical composition and evolutionary journey appear profoundly alien. Atlas offers an exceptionally rare window, enabling scientists to directly juxtapose theoretical frameworks with observable reality.
It provides a unique laboratory to probe and validate models concerning the birth of stars, the intricate chemistry governing planetary formation, and how complex organic molecules evolve under conditions vastly different than those within our own solar system. Ultimately, the concealed heart of 3 Atlas embodies a potent blend of profound mystery and immense scientific promise. It stands as a relic from a distant stellar system, one we may never physically explore, a meticulously preserved archive of interstellar chemical history frozen within the void. The very presence of an irradiated outer crust, combined with the tantalizing possibility of untouched interior material, fundamentally challenges established conceptions. It compels astronomers to reconsider prevailing notions about cometary nature, the mechanisms enabling interstellar travel for such bodies, and the astonishing diversity of chemical evolution processes occurring throughout the galaxy. Each distinct spectral signature, every sudden emission burst, and each observed outflow of gas represents a fragment of an ancient narrative, patiently waiting to be deciphered and understood. As Atlas gradually moves away from the Sun's influence, we bear witness to an extraordinary and tangible connection forged across the immense gulf between stellar systems.
The enigmatic blue luminescence, the substantial outflows of water vapor, the conspicuous absence of a traditional dust tail, and the evidence of solar radiation sculpting its surface, all these elements weave together a single, sweeping narrative. This narrative spans billions of years and traverses trillions of kilometers. Beneath these observable phenomena, the hidden core potentially contains the most astonishing revelations of all. It may hold the original chemical fingerprint of a distant world, offering humanity its first genuine glimpse into the nature of a star system that, until now, has remained entirely beyond our physical reach. The appearance of Comet Atlas serves as a powerful reminder that the universe is vast, profoundly mysterious, and possesses an endless capacity for invention. Within the fleeting moments our instruments can capture its passage, this celestial visitor imparts invaluable lessons concerning fundamental chemistry, the nature of radiation, and the intricate processes of planetary formation. These revelations actively challenge established scientific assumptions and significantly broaden our understanding of cosmic phenomena. It demonstrates unequivocally that interstellar travel transcends the confines of human-made spacecraft. This remarkable journey is a natural occurrence, capable of transporting the encoded secrets of distant alien worlds across the immense empty void between stars. Consequently, it offers humanity a unique and irreplaceable window into the hidden processes and diverse compositions that would otherwise remain entirely beyond our direct encounter. The comet's entire narrative, its long journey through space, the dramatic transformation it undergoes as it nears our star, and the secrets locked within its concealed core, ultimately converges to tell a profound story of cosmic endurance. At the very center of Atlas lies the preserved history of another, long-vanished star. It functions as a vast, frozen chemical archive, meticulously kept for countless eons. Modern astronomical techniques have now partially revealed this hidden record. Through meticulous study, we gain far more than knowledge about a single, extraordinary interstellar object. We acquire crucial insight into the universal processes that shape planetary systems scattered across the galaxy. This experience stands as a profound reminder of our intrinsic connection to the broader universe and the truly remarkable stories that occasionally arrive at our cosmic doorstep. These narratives are written not in ink, but in ice, dust, and the persistent traces of cosmic rays. As the global community witnessed Comet Atlas blaze past its closest approach to the Sun, perihelion, another, more subdued debate was simultaneously unfolding. This debate touched upon the very essence of scientific investigation itself, the critical question of access to the data being collected.
The observations pouring in from an impressive array of telescopes, encompassing both those stationed in orbit and powerful ground-based installations, represented an extraordinary treasure trove of information. Every photon meticulously recorded, every subtle spectral line painstakingly analyzed, and every single frame captured across the infrared and ultraviolet spectrums held the potential to unlock profound secrets about a guest arriving from another star system. Yet, a significant portion of this invaluable cosmic data remained tightly controlled by various agencies and institutions, creating barriers that limited access for the wider scientific community. Against this backdrop, Professor Avi Loeb, the esteemed former chair of Harvard University's astronomy department, emerged as a leading and passionate voice in this critical debate. Through formal statements and public commentary, Professor Loeb advocated forcefully for the immediate and unconditional release of all scientific data related to the interstellar object designated Atlas. He argued compellingly, "We are witnessing a phenomenon that fundamentally transcends the interests of any single institution. Every observation, every measurement, regardless of how preliminary or incomplete, ultimately belongs to humanity itself. This comet is not merely an object, it is a message delivered across the vast interstellar distances. Restricting access to its data actively hampers our collective pursuit of understanding." Professor Lowe's stance found strong resonance with numerous astronomers who have long championed the principle of open data policies within the scientific realm. In the contemporary era of science, transparency is widely regarded as not just an ethical imperative, but also a crucial driver for accelerating discovery and progress. When data flows freely, independent research teams can rigorously cross-verify each other's findings, explore diverse interpretations and hypotheses, and seamlessly combine observations gathered from multiple sources. Such collaborative synthesis is particularly vital for an object as unprecedented and extraordinary as Atlas. This level of cooperation could very well be the decisive factor separating mere speculation from genuine comprehension. Nevertheless, the question of data access proves to be far from straightforward, presenting complex challenges that require careful consideration. Institutions such as NASA, the European Space Agency, and other bodies responsible for managing observations typically function under stringent protocols that regulate the dissemination of data. These protocols exist to safeguard against potential misinterpretations that could arise from the premature release of unverified or preliminary findings. Additionally, there are practical reasons for this cautious approach.
The sheer volume of raw data necessitates meticulous calibration, processing, and contextual analysis before it can be genuinely beneficial to the wider scientific community. The unregulated release of raw data may lead to confusion, inaccurate reporting, or even misrepresentation of discoveries. Despite these concerns, the case for transparency in the context of the Atlas object is strong. This is an entity that has traversed interstellar space, originating from a distant stellar system, carrying with it clues about chemistry, planetary formation, and cosmic evolution. Instruments like the James Webb Space Telescope, SOHO, GO, and ground-based arrays have collectively gathered a multi-dimensional data set that could potentially revolutionize our understanding of interstellar objects. Every delay in data release translates to a delay in discovery, an opportunity missed to refine models, test theories, and expand our comprehension of the cosmos. Some astronomers have also raised ethical considerations. They posit that when an object makes its way from outside the solar system, it can be considered, in a sense, to belong to all of humanity. Thus, the scientific obligation to share findings transcends mere professional duty.
The moral imperative of open data in astronomy cannot be overstated. Deliberately restricting information solely to bolster institutional prestige, secure funding advantages, or serve national pride fundamentally contradicts the essential collaborative ethos that drives contemporary astronomical discovery. This principle was forcefully reiterated by Alo. The arrival of a cosmic visitor like Atlas carries a profound responsibility to guarantee that every researcher, every aspiring student, and every engaged citizen scientist possesses the genuine opportunity to participate in its study. Conversely, advocates for cautious data handling voice significant concerns about premature release. They warn that the rapid dissemination of information, particularly to audiences lacking specialized expertise, creates fertile ground for misunderstanding. Interstellar objects are inherently intricate systems. Their spectral signatures can be highly ambiguous. Their variations in brightness, light curves, are often challenging to decipher, and their observed behaviors frequently defy established precedents. Without crucial contextual information, sharing initial findings risks propagating inaccurate assertions, fueling sensationalized headlines, or embedding scientific errors within the public record. Space agencies, these proponents contend, bear the complex mandate of balancing the principle of openness against the absolute necessity of scientific precision. Despite these cautions, the truly unprecedented characteristics of Atlas have amplified demands for transparency. In response, some research groups have adopted a middle path.
They are releasing carefully processed subsets of data, enabling independent verification and cross-checking, while safeguarding the original, uncalibrated observations from unrestricted access. Simultaneously, others have published early-stage analyses accompanied by exhaustive methodological descriptions. This approach ensures that even when the foundational raw datasets remain restricted, the derived conclusions remain subject to rigorous scrutiny, independent reproduction, and further scientific advancement. This ongoing debate has resonated far beyond specialized scientific circles, igniting conversations within public forums as well. It highlights the critical intersection of scientific inquiry, governmental policy, and ethical considerations in an era defined by collective global curiosity. Avi Loeb's passionate advocacy significantly illuminated the far-reaching consequences of interstellar research. While comets originating within our own solar system captivate us with their wonders, they adhered to discernible chemical and physical patterns. Atlas, however, stands apart. It embodies the profound possibility of entirely novel chemical compositions, exhibits unusual isotopic ratios, and displays structural anomalies meticulously shaped over eons within the void of interstellar space. The act of withholding even temporary data access carries substantial risk, potentially delaying crucial insights that could profoundly inform diverse scientific disciplines. These insights could reshape our understanding in astrochemistry, planetary science, and even illuminate the specific galactic conditions essential for life. This intense scientific debate resonated through major conferences, scholarly journals, and advisory board deliberations. Younger astronomers argued with fervor for immediate, open access to data. They emphasized that only collaborative analysis spanning multiple institutions and nations could maximize the immense scientific return from studying Atlas. Veteran scientists, though sympathetic to the drive for openness, underscored the critical necessity of thorough verification and rigorous peer review. They cautioned that drawing premature conclusions based on unverified data could irreparably undermine the entire project's credibility and long-term scientific standing. This fundamental tension between unrestricted openness and careful data control reflects a defining characteristic of contemporary science itself.
It represents a constant push and pull between the democratization of knowledge and the vital responsibility required for its stewardship. Parallel to these institutional discussions, numerous citizen science groups voiced their frustration. Enthusiasts equipped with modest telescopes or computational models felt increasingly sidelined, unable to meaningfully engage with the extraordinary opportunity presented by Atlas due to the restricted data access.
For these dedicated individuals, the debate transcends mere academic discussion. It represents a significant barrier to their participation and contribution at the very frontier of discovery. The unfolding saga of observing one of the most extraordinary astronomical phenomena occurring in our era stands as a profound human endeavor. The narrative surrounding these celestial bodies resonates so deeply with our collective imagination, precisely because it offers a tangible link to the vast, mysterious cosmos beyond our own solar system. Some voices in the scientific community argue that restricting access to the observations diminishes this crucial connection, severing a vital bond between humanity and the wider universe. These ethical considerations deepen significantly. They compel us to confront fundamental questions about the obligations of researchers when encountering phenomena of truly global importance. Should breakthroughs that fundamentally challenge our understanding of the universe be treated as proprietary knowledge, retained within institutional frameworks until comprehensive analysis is complete? Or should the paramount priority be the unfolding process of collective exploration, open to all? Resolving these dilemmas proves remarkably difficult. They strike directly at the core of what it means to practice science within our interconnected world. Silent and shrouded in mystery, this distant celestial visitor has become a powerful catalyst for reflection on these very issues. Ultimately, the debate surrounding the release of collected data transcends mere bureaucratic procedure. It mirrors the evolving landscape of scientific collaboration, characteristic of the 21st century. The journey of this object, traveling from its distant star system to our very instruments here on Earth, is a story that truly belongs to all of humanity. The choices made in the weeks and months following the comet's closest approach to the Sun will establish important precedents for how humanity handles future interstellar visitors. These decisions will define the delicate balance between institutional stewardship, the drive for individual discovery, and the imperative of public access. Within this critical context, the perspectives of scientists such as Dr. Avery carry substantial weight. Their insights extend far beyond the specifics of this single celestial event. They serve as a vital reminder that the advancement of science flourishes not in isolation, but through dynamic dialogue, rigorous scrutiny, and our shared fundamental curiosity about the unknown. The arrival of Atlas compels us to probe beyond merely cataloging its composition or predicting its behavior. It challenges us to examine how scientific inquiry adapts when the universe presents something utterly unprecedented. The debate surrounding the release of data captured during its passage holds almost equal significance to the observations themselves.
Just as the comet's trajectory etches its path across the celestial canvas, this internal discourse shapes the very trajectory of discovery. As weeks turned into months, a delicate balance gradually emerged. Select datasets were cautiously released to researchers operating under formal collaborative agreements and trusted protocols, while other, more complex sets remained under tightly controlled access pending further calibration and validation. Simultaneously, vigorous discussions unfolded across public portals, preprint servers, and open-source platforms. These exchanges illuminated the persistent, intricate tension inherent in modern science, the urgent demand for transparency versus the meticulous pursuit of precision. Each phase of this evolving process reinforced a fundamental principle. The unfolding narrative of Atlas is not solely inscribed in the primordial ice and luminous gases of its nucleus, but equally etched within the very structures ethical frameworks and established practices governing contemporary scientific research. Observing Atlas through our instruments, we are confronted by a dual enigma. One mystery lies deep within its core, a physical secret preserved for billions of years. The other resides in the human realm, concerning the decisions made and the knowledge it promises to unlock. These two mysteries are inextricably linked, serving as a constant reminder that science, however profound its cosmic ambitions, remains fundamentally a human endeavor. While debates regarding data access persist, the comet itself continues its silent journey, utterly unmoved by our deliberations. Yet it offers profound clues to those possessing the patience, insatiable curiosity, and unwavering integrity to decipher them. Thus, Atlas stands as both a genuine visitor from another star system and a mirror, reflecting back the intricate choices, profound responsibilities, and distinct priorities of the scientific community that seeks to understand it. As humanity examines the data gathered from this extraordinary celestial traveler, deliberates on the very nature of access to its revelations, and strives to harmonize the imperative for open scientific discourse with the necessity of rigorous verification, the significance of these endeavors may well prove as profound as the chemical and physical insights it offers. The study of Atlas serves as a mirror, reflecting not only the complexities of a distant stellar system, but also illuminating fundamental aspects of our own species, our innate curiosity, the ethical frameworks guiding our exploration, and our remarkable capacity for global collaboration in the relentless pursuit of understanding. As the comet 3I Atlas journeys away from the sun's intense heat, astronomers spanning the globe are contending with a deceptively simple yet deeply profound inquiry. What unfolds next?
The spectacular display witnessed during its closest approach to our central star, known as the perihelion outburst, provided a tantalizing glimpse into its truly extraordinary and unpredictable behavior. Yet, the precise future trajectory of this interstellar guest and the extent of its anticipated activity remain veiled within a shroud of considerable uncertainty. Unlike comets originating within our own solar system, bound by the familiar gravitational dance dictated by our local celestial mechanics, Atlas is not constrained by established patterns. The precise manner in which its irradiated outer layer responds to intense solar radiation, the inherent structural integrity of that crust, and the exact composition residing within its core are variables that elude definitive prediction. Historically, the behavioral patterns exhibited by comets existing within our solar system following their perihelion passage tend to follow relatively predictable sequences. Many such comets, having reached their closest point to the Sun, typically begin to fade gradually as the solar energy input diminishes. The exhaustion of surface ice and a consequent reduction in the outgassing of volatile materials are common features of this decline phase. However, in the case of Atlas, astronomers exhibit pronounced caution. The dramatic perihelion outburst observed suggests the potential existence of hidden reservoirs of volatile material still entombed beneath its surface. These concealed pockets hold the latent potential to trigger further, unexpected eruptions, sudden, localized bursts of gas and dust, phenomena that defy conventional expectations and fundamentally challenge our current comprehension of comet physics and behavior.
Astronomers have carefully outlined several plausible trajectories for the comet's development following its perihelion passage. One anticipated outcome involves a steady, gradual reduction in brightness. This scenario proposes that the majority of volatile ices situated near the surface have been significantly depleted after the intense perihelion encounter. Consequently, subsequent cometary activity would diminish consistently over time. Within this context, the comet would progressively dim over several months, eventually reaching a point where its faintness renders it undetectable by most ground-based or space-based telescopic instruments. While such a fading process might appear relatively ordinary after the spectacular display witnessed during perihelion, even this declining phase offers significant scientific value. Meticulously tracking the decline in activity provides crucial insights for researchers. This data can help unravel the intricate distribution of subsurface ices within the nucleus and significantly refine theoretical models describing how cometary materials sublime under the extreme thermal conditions experienced so close to the Sun. Conversely, another distinct possibility involves the comet continuing to experience dramatic outbursts. This scenario hinges on the likelihood that fractures developing within the irradiated crust expose additional, deeper layers containing volatile material. If this occurs, Comet Atlas could persistently generate sudden, intense increases in brightness, transient emissions of various wavelengths, and unpredictable jets of gas propelled by subliming ices. These ongoing potential for unpredictable bursts presents a significant challenge to astronomers attempting to forecast its behavior accurately. Unlike the more predictable decline in activity observed in standard comets, the behavior of Comet Atlas remains distinctly unpredictable. Its outbursts may occur sporadically and seemingly at random intervals, defying simple forecasting models. These unpredictable eruptive events hold particular fascination for astronomers. Each sudden surge acts like a natural window, momentarily revealing glimpses into the comet's interior. Through careful analysis of the materials ejected during these bursts, scientists can infer crucial details about the composition, structure, and distribution of substances previously concealed deep within the nucleus. A more dramatic scenario involves the comet undergoing fragmentation. The intense structural stresses generated as Atlas nears its closest approach to the Sun, perihelion, combined with the uneven nature and hardened state of its outer crust, could prove too much for parts of the nucleus to withstand. Significant fragments might eventually break away. While fragmentation is a phenomenon observed in comets, it is not necessarily common.
For an interstellar visitor like Atlas, however, such an event would present truly unique scientific opportunities. It would allow researchers to study the fundamental mechanics of how the nucleus responds to stress and breaks apart, while simultaneously revealing the composition of the separate pieces that are created. Crucially, multiple fragments of the comet could exhibit diverse behaviors. Each piece might release distinct chemical signatures into space, providing valuable clues. This variation would directly demonstrate the internal heterogeneity within the comet's core, potentially reflecting the complex conditions present during its own formation far from our solar system. If fragmentation does indeed occur, astronomers recognize the critical need for rapid and coordinated observation efforts. Scientists would need to track each individual fragment swiftly and efficiently, ensuring that no fleeting scientific opportunity offered by these pieces is missed. To prepare for these potential scenarios, observational campaigns have been meticulously planned and are now actively underway. Space-based instruments, including renowned observatories such as Hubble, Webb, and SOHO, remain on constant high alert, ready to capture crucial data untroubled by atmospheric interference. Simultaneously, a global network of ground-based telescopes, stretching from the arid expanse of the Atacama Desert to the clear skies of Mauna Island, continues to vigilantly track Atlas's precise trajectory through space. The successful integration of data from these diverse observational platforms, both spaceborne and terrestrial, is deemed absolutely crucial for maximizing the scientific return and comprehensively understanding this extraordinary celestial visitor. Space-based telescopes offer a unique vantage point, capable of detecting emissions and intricate details in the immediate vicinity of the Sun that remain obscured from terrestrial observation due to atmospheric interference and technological constraints. Meanwhile, ground-based observatories contribute invaluable long-term monitoring, tracking subtle fluctuations in brightness, shifts in spectral composition, and potential fragmentation events over extended periods. When combined, these complementary approaches create a unified network adept at capturing both anticipated phenomena and unforeseen developments. Astronomers are also leveraging the potential for unexpected discoveries through serendipitous observations, relying on both professional and amateur astronomers to contribute data. Even modest amateur telescopes play a critical role in documenting gradual fading or intermittent bursts of activity, complementing high-tech instruments. By synthesizing observations from diverse sources, researchers can construct high-frequency datasets that expose fleeting events invisible to isolated instruments.
This collaborative methodology has evolved into a defining feature of contemporary astronomical research, enabling the global scientific community to swiftly adapt to the erratic behaviors exhibited by interstellar objects. Predicting the dynamics of objects like Atlas necessitates meticulous modeling of their central bodies or nuclei. Advanced thermal simulations, structural integrity assessments, and chemical analyses are employed to anticipate potential fracture points and identify regions retaining volatile materials. The irradiated crust, extensively studied in prior research, remains a focal point in these models. Its variable thickness, structural resilience, and uneven composition directly determine the probability of explosive outbursts or disintegration. By deciphering these factors, astronomers aim to anticipate periods of heightened activity and strategically schedule observations to maximize scientific yield. This multifaceted approach underscores the importance of integrating theoretical models with empirical data, ensuring a comprehensive understanding of these enigmatic celestial travelers. The comet's passage through the inner solar system introduces significant complexity to its journey. Its trajectory is profoundly shaped by gravitational interactions not only with the Sun but also with the planets, alongside the subtle yet crucial influence of minor bodies. As Comet Atlas recedes outward, it undergoes a dramatic transition. It moves away from the intense solar radiation experienced at perihelion, the point of closest approach to the Sun, and enters the colder, more stable environment of the outer solar system. This shift in conditions is likely to diminish active surface phenomena, such as jets and outgassing. However, it may simultaneously illuminate slower, less obvious processes. These could include the delayed sublimation of ice buried deep beneath the surface, only now exposed to the persistent cold, or the gradual relaxation of immense structural stresses built up within the comet's nucleus during its earlier, more turbulent passage near the Sun. Closely monitoring these evolving processes provides invaluable data, crucial for understanding the long-term evolution of interstellar objects traversing our cosmic neighborhood. The inherent unpredictability of Comet Atlas serves as a powerful reminder of how incomplete our knowledge remains regarding interstellar comets. Each observation challenges established assumptions, pitting our understanding against the realities of its unique chemical composition and mechanical behavior. The dramatic outburst observed near perihelion was particularly startling, demonstrating conclusively that an object forged around a distant, unfamiliar star can exhibit behaviors entirely unlike those seen in comets native to our own solar system. Consequently, monitoring Comet Atlas after its perihelion passage is far more than simply documenting a fading celestial body.
It is an essential scientific mission, fundamental to deciphering the core processes that govern the evolution of objects originating in stellar environments vastly different from our own. This complex endeavor has made collaboration and communication absolutely vital.
Robust data-sharing protocols, seamless coordination between observatories scattered across the globe, and the rapid dissemination of findings enable scientists to react swiftly, often in near real time, to any unexpected developments or subtle changes in the comet's behavior. This coordinated, worldwide effort reflects the immense scientific stakes involved in studying these rare visitors from beyond our solar system. Atlas is far more than a mere scientific curiosity. It is a singular window into the history and chemistry of another star system. Every day that it is observed, every new emission recorded, contributes pieces to a puzzle that may never fully resolve, yet promises to deepen our understanding of the universe. Ultimately, the post-perihelion future of 3 Atlas remains a narrative of uncertainty and anticipation. Will it fade quietly, its brilliance and memory preserved in telescope archives? Will it continue to surprise with sudden outbursts, a comet that refuses to conform to expectations? Or will it fragment, scattering clues about its interior across the solar system? Each scenario carries profound scientific implications, offering insights into interstellar chemistry, radiation processing effects, and the intriguing dynamics governing icy bodies within the environment of a foreign star system. The story of this remarkable interstellar visitor remains very much unfinished.
New, critical chapters are being written in real time, unfolding before the watchful eyes of our most sophisticated telescopes and scientific instruments. When we observe Atlas, we witness far more than the passage of a comet. We are witnessing a profound cosmic narrative spanning origins, dramatic transformation, and the inherent unpredictability of celestial mechanics. Every sudden increase in brightness, every powerful jet of escaping gas, and every minute alteration in its path narrates a story etched across unimaginable distances of interstellar space and the vast expanse of cosmic time. As astronomers continue their meticulous observations, calculations, and theoretical explorations, and as space enthusiasts follow along, one fundamental truth emerges clearly. Whatever occurs next in the journey of Atlas, this comet will undoubtedly continue to defy expectations, shed new light on our current comprehension of the cosmos, and deepen our sense of connection to the immense universe beyond our solar system. Atlas's voyage through our system has achieved more than simply captivating astronomers. It has compelled a fundamental reassessment of our existing knowledge regarding objects originating beyond our stellar family. For many years, the sporadic arrival of comets and asteroids from interstellar space has presented only a tantalizing curiosity to the scientific community. Atlas, however, has proven to be something profoundly more significant. It stands as a dynamic natural laboratory, a tangible fragment hailing from a distant stellar system. This visitor directly challenges the established foundations of planetary science, the physics of comets, and the chemistry of the cosmos itself. Looking back at the discovery of Oumuamua in 2017, we recognize a precedent. Atlas now represents a far more substantial and scientifically rich encounter, demanding deeper study and offering greater revelation than its predecessor.
The sheer volume and depth of data gathered during Atlas's close approach have fundamentally rewritten our understanding of these cosmic intruders. This wealth of information now illuminates not only their paths and forms, but also their complex chemistry, patterns of activity, and the intricate evolutionary histories encoded within them. One of the most significant revelations emerged from Atlas's dramatic outburst as it passed closest to the Sun. This event underscored a crucial realization: interstellar objects may exhibit behaviors utterly alien to anything observed within our own solar system. The sudden explosive increase in brightness, the complete lack of a dust tail typically associated with comets,
the detection of unusual spectral signatures indicating unfamiliar materials, and the observation of an irradiated, altered outer layer collectively demonstrate that we cannot simply assume our solar system analogs apply universally. These objects are forged under conditions vastly different from those at home, subjected to intense cosmic rays, the radiation of distant stars, and gravitational forces operating in star systems unlike our own. Each interstellar visitor, therefore, stands as a unique, naturally occurring experiment, carrying the imprints of the diverse environments where they originated. Comparing Atlas and similar objects directly to familiar comets within our solar system highlights the profound scale of this difference, revealing that our celestial neighborhood represents only one possible outcome among countless cosmic variations. While comets within our solar system exhibit remarkably consistent behaviors as they near the Sun, predictable sublimation patterns, the formation of characteristic tails, and distinct gas emissions near their closest approach, the interstellar visitor designated Atlas has utterly confounded our most sophisticated predictions. Its anomalous blue-shifted emissions, astonishingly rapid water loss, and truly episodic bursts of activity paint a picture of chemical and structural processes that have undergone profound evolutionary changes over billions of years, all under conditions fundamentally alien to our own stellar environment. These striking distinctions compel a fundamental reevaluation of models concerning comet formation and evolution, a reevaluation that extends far beyond mere interstellar wanderers. Crucially, they challenge our deepest assumptions about the very universality of chemical and physical processes operating throughout the galaxy. The ramifications of studying Atlas reach even further, touching the core of how planetary systems come into being. This comet offers indirect yet compelling evidence of the vast diversity of conditions that exist around other stars.
If the composition and internal structure of this object prove markedly different from any comet we have ever observed within our own system, then it stands to reason that the very planets forming within those distant stellar systems may themselves possess characteristics significantly distinct from Earth or Jupiter. The ratios of volatile compounds present, the prevalence of complex organic molecules, and the inherent structural integrity of icy bodies in other systems may all vary dramatically. These variations are likely sculpted by the unique interplay of the local radiation environment, the specific chemical makeup of the host star, and the intricate dance of orbital dynamics within each nascent planetary system. In this profound sense, Atlas transcends the role of a mere celestial visitor. It acts as a cosmic messenger, whispering secrets about the infinite permutations of planetary architecture possible throughout the galaxy. Furthermore, interstellar objects like Atlas serve as invaluable informants for our understanding of galactic chemistry on a grand scale. Every single element, every complex molecule, every trace compound they carry across the void of interstellar space represents a fleeting snapshot, a frozen moment revealing the specific chemical conditions prevailing within another star system before those conditions were irrevocably altered. Through meticulous analysis of isotopic ratios, the subtle signatures of atomic variation, alongside the detection of complex organic molecules and the study of material transformation under relentless cosmic ray bombardment, scientists unlock profound understanding of how chemical elements are dispersed throughout our galaxy. The enigmatic interstellar object, denoted as Atlas, with its irradiated outer layer potentially shielding a pristine interior, serves as a crucial link. It bridges the tangible observations gathered by astronomers with the intricate theoretical frameworks used to model the galaxy's ever-changing chemical composition over eons. This discovery carries significant philosophical weight. Humanity, gazing upwards for millennia, has perpetually questioned the uniqueness of our solar system and the rarity of conditions permitting life's emergence. Atlas provides concrete proof derived from a truly alien environment.
It stands as a powerful reminder that stars, planets, and comets are not isolated celestial events, but integral components woven into a vast, interconnected galactic ecosystem. The observed behavior, unique chemistry, and evolutionary path of Atlas directly challenge the long-held assumption that phenomena witnessed within our own solar system can be universally extrapolated to govern the entire cosmos. Each visitor from the interstellar void imparts a vital lesson in cosmic humility, simultaneously revealing the extraordinary richness of the universe and exposing the inherent limitations of our current models.
Consequently, the methods for observing the heavens are undergoing significant transformation. Astronomers now actively acknowledge that interstellar objects may defy the predictable patterns inherent to solar system-based dynamics. Survey programs are being fundamentally revised to detect faint, fast-moving interstellar passers-by, while space-based observatories are being assigned the critical task of high-frequency monitoring. This heightened vigilance aims to capture fleeting phenomena such as unexpected outbursts or unusual structural anomalies that were previously overlooked. Emerging space missions are now envisioned with a distinct purpose: to intercept and analyze interstellar objects directly through spacecraft equipped for close approaches, specimen gathering, or prolonged observation. The recent arrival of Atlas has expedited these plans, propelling the development of a new era in interstellar exploration. Yet Atlas's erratic trajectory following its closest approach to the Sun has highlighted the boundaries of our existing understanding. Its post-perihelion behavior remains enigmatic, and critical inquiries, such as the composition of its nucleus or the potential presence of intricate organic compounds, may only be resolved through direct physical examination. Nevertheless, the observations gathered thus far have fundamentally shifted scientific perspectives, compelling astronomers to regard interstellar objects not as ordinary comets merely passing through our solar system, but as entities forged in distant cosmic environments. These travelers exhibit chemical complexity and evolutionary histories that challenge human imagination, suggesting they carry secrets of planetary systems beyond our own. The presence of 3 such objects named Atlas thus presents both a remarkable scientific opportunity and a profound philosophical inquiry. It urges us to refine our theoretical frameworks, question long-held assumptions, and confront the vast diversity of planetary systems scattered across the galaxy. This phenomenon fosters a dynamic interplay between empirical observation and theoretical interpretation, bridging raw data with nuanced understanding while balancing humanity's curiosity with scientific prudence. Furthermore, it underscores the indispensable role of global scientific cooperation as researchers worldwide unite to monitor, analyze, and decipher the origins of an object that transcends the boundaries of our solar system, becoming a bridge between our local celestial neighborhood and the infinite expanse of the cosmos. Atlas emerges as a profound testament to the boundless complexity of interstellar space, inviting humanity to reconsider the very fabric of our cosmic neighborhood. Its discovery echoes the earlier whispers of Oumuamua, which first hinted at the extraordinary phenomena lurking beyond the confines of our solar system.
Yet Atlas transcends those initial glimpses, offering a tangible encounter that defies conventional expectations. Through meticulous observation and spectral analysis, it unveils a kaleidoscope of chemical diversity, revealing molecules and compounds that challenge our understanding of stellar and planetary processes. Each spectral line deciphered, each trajectory calculated becomes a thread in a larger narrative, one that bridges our solar system to the vast, interconnected tapestry of the Milky Way. This celestial messenger is not merely a fleeting curiosity, but a harbinger of a new paradigm. The realization that interstellar objects like Atlas are not rare anomalies, but rather emissaries traversing the galaxy, compels us to reimagine our place in the cosmos. They carry the fingerprints of distant star systems, offering clues about galactic chemistry, planetary formation, and the dynamic forces that sculpt worlds. These objects, once dismissed as anomalies, now stand as critical evidence of a universe teeming with movement, transformation, and hidden connections. Their study forces a reevaluation of long-held assumptions, pushing scientists to refine models of planetary systems and cosmic evolution. In the years ahead, Atlas will serve as a cornerstone for exploration, guiding missions to intercept or analyze similar visitors. Its lessons will inform theoretical frameworks, helping to unravel the mysteries of how planets form, how life might arise in distant environments, and the mechanisms that govern the dispersal of matter across light years. Though its passage through our solar system was brief, its legacy will endure, a catalyst for inquiry that reshapes the scientific imagination. It compels us to embrace uncertainty, to pursue questions we have yet to formulate, and to recognize that the universe, vast and enigmatic, continues to reveal its secrets one interstellar traveler at a time. The 3-Eye Atlas, with its unpredictable nature, serves as a constant reminder that the cosmos is far stranger and richer than our imaginations often allow. It challenges our preconceived notions, piques our curiosity, and demands our attention. Through the study of this interstellar visitor, we not only unravel the mysteries of a comet originating from beyond our star system, but also gain profound insights into the processes that shape our galaxy and, ultimately, the universe itself. There exists a deeply magnetic allure to encountering an interstellar traveler like the 3-Eye Atlas. Beyond the technical analyses, spectra, and intricate models, there lies a deeper, almost ineffable human reaction: wonder. For countless millennia, humanity has gazed upwards, contemplating the vastness beyond our fragile world. We have woven tales around stars, comets, and planets, infusing them with mythology, imagination, and insatiable curiosity.
And then, on occasion, the universe offers us a tangible response, a piece of another world, traveling billions of kilometers through the void, suddenly appearing in our celestial neighborhood. Such is the extraordinary nature of Atlas. From the very instant its peculiar trajectory was detected, the comet captured the public's imagination. Unlike the familiar comets that follow predictable paths, Atlas arrived as something entirely unknown, a messenger from a distant star system, carrying with it clues about chemistry, formation, and cosmic history that had never before been accessible to humans. The object's approach, known as its perihelion outburst, marked a dramatic surge in brightness, accompanied by a puzzling absence of a dust tail. These extraordinary scientific phenomena were moments of awe that captivated the world. News outlets, social media platforms, and online forums were abuzz with speculation, images, and questions, reflecting a global sense of anticipation and curiosity. For scientists, the fascination was both professional and deeply personal. On one hand, there was the meticulous work of analysis, examining spectra, studying light curves, and modeling the ejection of gas and dust. On the other hand, there was the emotional response of witnessing something utterly unprecedented. The blue-shifted emissions, accelerated water loss, and the behavior of the irradiated crust all defied expectations. Astronomers have described moments when the data reveal phenomena so unusual that they are compelled to pause and reflect on the scale of what they are observing. It is both exhilarating and humbling, a reminder of how much remains unknown. There is also a philosophical dimension to this fascination. The object challenges our perception of time and distance in ways that are difficult to grasp. The object we observe today departed its home system billions of years ago. It has drifted through the cold, dark void of interstellar space, bombarded continuously by cosmic rays, shaped by gravitational interactions and influenced by processes entirely alien to our solar system. By observing it, we are not just looking at light traveling millions of kilometers. As we delve into the profound history of another star, we observe a glimpse of cosmic evolution that has endured the relentless challenges of interstellar space for countless millennia. This perspective is profoundly inspiring, serving as a humbling reminder of the immense scales of time and space within which our lives unfold. The emotional resonance of this discovery transcends the boundaries of professional circles, reaching out to the broader public. For many, Atlas acts as a bridge between the realms of imagination and reality. Its journey ignites a series of questions that are both scientific and existential. How many other planetary systems exist out there? Could objects like Atlas have once harbored the materials necessary for seeding life?
Are the conditions that allowed life to emerge on Earth common or exceedingly rare? In this context, Atlas is more than just a comet. It is a conduit for cosmic reflection, a phenomenon that compels humanity to ponder its place within the galaxy. A significant source of fascination with Atlas lies in its unpredictability. Unlike the regularity of planetary orbits or the predictable celestial events such as eclipses or solstices, Atlas behaves in ways that cannot be fully anticipated. Its brightness surges unexpectedly, its gas emissions fluctuate unpredictably, and its interior remains concealed beneath a radiation-processed crust. The uncertainty surrounding Atlas heightens the drama, capturing imaginations precisely because it mirrors the universe's inherent unpredictability. We are confronted with phenomena that are far larger, older, and stranger than ourselves, and our sense of wonder grows in direct proportion to our inability to fully control or predict them. Engaging with Atlas represents a profound professional privilege for scientists. These interstellar visitors represent an extraordinary rarity within our cosmic neighborhood. The chance to scrutinize one such object with multiple sophisticated instruments operating simultaneously, both from Earth and aboard space-based observatories, constitutes an opportunity that may remain unmatched for many decades, potentially centuries. Each individual measurement taken, every spectral analysis conducted, and every single frame captured offers a unique and vanishing glimpse into processes that commenced eons before our own planet even formed. This remarkable privilege inherently carries a deep sense of responsibility. The invaluable data being gathered now will serve as the foundation for refining predictive models, will directly inform the planning of future astronomical investigations, and holds the potential to fundamentally reshape our comprehension of planetary system formation and the intricate chemistry pervading the galaxy for generations to come. Yet the profound human fascination extends beyond the purely scientific. There exists an almost poetic resonance in the concept that a fragment of ice and rock forged around a distant star light years away could traverse the immense expanse of the galaxy and momentarily intersect with our own solar system. Atlas becomes, for a fleeting moment, a tangible connection bridging vast cosmic distances, serving as a powerful reminder that our solar system is not an isolated entity, but rather an integral part of a much broader, interconnected cosmic ecosystem. Its extraordinary journey compels reflection on the staggering scales of space, the immense distances involved, and the concept of longevity that operates on galactic timescales, a perspective offered by few other celestial phenomena.
By observing Atlas, we are profoundly reminded of the universe's staggering vastness and ancient history, while simultaneously experiencing the personal significance of witnessing a fragment from that distant cosmos intersect with our own human experience in such a direct and tangible way. Public fascination is further intensified by the deep sense of mystery surrounding Atlas.
Its behavior deviates significantly from that of any comet previously documented, leaving even the most seasoned astronomers genuinely perplexed and eager to uncover the reasons behind its unique characteristics. The unpredictable nature of celestial phenomena transforms what might otherwise seem like a distant scientific subject into a living narrative, a story unfolding in real time, accessible to all who dare to witness it. Each passing moment offers new revelations, inviting observers, whether from distant observatories or humble backyards, to engage, interpret, and dream. The comet becomes more than an astronomical object. It crystallizes into a shared human experience, uniting professional researchers, passionate amateurs, and countless members of the public in a collective moment of awe. It serves as a humbling reminder of the extraordinary reach of human curiosity and ingenuity. Through an intricate network of telescopes, precision spectrographs, and advanced space-based observatories, humanity extends its perception into the void, gathering data with meticulous care. Yet it is the human mind that breathes life into these signals, translating faint glimmers of light into models of cosmic processes, weaving theories from fragments of evidence, and daring to imagine realms beyond direct observation. The true allure lies not merely in the comet itself, an ephemeral amalgam of ice, dust, and vapor, but in the profound dialogue it sparks between humanity and the cosmos. This interplay reflects our enduring quest to understand, to situate ourselves within the vastness of existence, and to seek meaning in a universe that remains both indifferent and profoundly inspiring. Ultimately, the comet's fleeting presence bridges the gap between the familiar and the unimaginable. It exists simultaneously as a tangible entity, composed of ancient ice and molecular complexity, and as a symbol of humanity's restless spirit, the unyielding drive to explore, to question, and to wonder. Its transient journey challenges preconceived notions, ignites a sense of shared connection to the stars, and underscores that even in an era defined by technological mastery, the cosmos retains the power to astonish, uplift, and move us to our core. As its luminous trail gradually dims against the backdrop of deep space, the comet leaves behind not just data, but a quiet testament to our place within the grand tapestry of the universe. Yet its legacy will transcend scientific achievement to embrace profound emotional significance.
It has illuminated aspects of interstellar chemistry, cosmic radiation, and cometary physics, offering humanity unprecedented insights into the mechanisms governing celestial bodies. At the same time, it has sparked a universal fascination, compelling us to reflect on our existence within an intricately linked cosmos. The human reaction to Atlas, marked by awe, insatiable curiosity, and introspection, is as pivotal as the empirical data it generated. This celestial phenomenon underscores a fundamental truth. Though physics operates through precise calculations, our engagement with the cosmos is inherently shaped by wonder, creative imagination, and the humbling realization of our minuscule presence against the backdrop of an unfathomably vast and ancient universe. With its peculiar beauty and enigmatic nature, Atlas beckons us to gaze upward and ponder the seemingly impossible. It disrupts conventional understanding, awakens dormant curiosity, and forges a connection to the sweeping narrative of cosmic evolution. As it gradually recedes into the abyss of interstellar space, its influence persists beyond the tangible remnants of light and matter. Its journey reverberates in the collective consciousness of humanity, echoing in minds, stirring hearts, and igniting imaginations worldwide.
When Atlas departs from the Sun's proximity, leaving behind the brilliance of its closest approach and the wealth of data gathered by our most advanced instruments, we are left with a bittersweet amalgam of revelations and unresolved inquiries. The saga of this interstellar traveler remains unfinished. Indeed, in numerous respects, the comet has imparted deeper lessons about the nature of uncertainty, the intensity of curiosity, and the boundaries of human comprehension than it has about its own physical makeup.
Yet, even these explanations, grounded in classical comet physics, fall short in accounting for the irregularity and extraordinary magnitude of its activity. There remains the tantalizing possibility that the nucleus conceals structures or compounds entirely alien to our experience, forged in the unique environment of another star. Another perplexing peculiarity lies in the absence of a dust tail, a feature universally expected from comets traversing our solar system. Instead of a sweeping trail of particles illuminated by sunlight, Atlas appeared as an elongated, glowing mass, its form defying conventional expectations. A remarkable phenomenon has perplexed both professional astronomers and advanced automated instruments, the absence of a dust tail in a particular comet. This enigma challenges our conventional understanding of comet formation and behavior, hinting that the surface composition, the structural integrity of the crust, or the mechanisms of outgassing may operate differently in interstellar objects. Each new image and each spectral reading has brought more questions than answers. The blue-shifted emissions have added yet another layer of mystery. Spectroscopic analysis has revealed the presence of carbon compounds and amidogen, which are indicative of sublimation processes commonly observed in comets. However, the intensity, timing, and distribution of these molecules in Atlas defy all precedents. The data suggest a complex internal chemistry shaped by both its original stellar environment and the cumulative effects of billions of years spent traversing interstellar space. Cosmic rays, which have penetrated tens of feet into the surface, have fundamentally altered the outer layers, creating a radiation-processed crust unlike anything previously observed in solar system comets. Understanding the interplay between these factors remains a significant challenge. Beyond the scientific curiosity, Atlas raises profound philosophical and existential questions. What does it mean that an object formed around another stellar system has traversed the galaxy to arrive, even if only briefly, within our observational range? Each observation is a connection to a distant history, an intimate glimpse into processes that have shaped a world entirely separate from our own. The existence of Atlas serves as a profound cosmic reminder. It illustrates that our solar system occupies but a single point within an immensity of space, a realm characterized by staggering scale, infinite variety, and unfathomable age. Countless other environments scattered across the galaxy have similarly witnessed the fundamental processes of matter coming together, undergoing transformation, and embarking on journeys through the void. The very presence of this remarkable comet directly challenges the notion of celestial isolation. It stands as tangible evidence that material originating from one stellar system can traverse the vast distances between them.
This galactic transit, we are increasingly realizing, holds the potential to deliver not only dust and rock, but perhaps even the seeds of complex ideas, fundamental molecules, or even nascent life, operating in ways we are only beginning to comprehend. Despite the substantial body of data gathered about Atlas, significant mysteries persist, waiting to be solved. What secrets lie hidden within the comet's ancient shadowed core? Could protected reservoirs of material, untouched by the ravages of cosmic radiation, exist beneath the altered outer layer? Such pristine pockets might hold invaluable clues about the unique chemical conditions present in the comet's distant, original stellar nursery, conditions far removed from anything we can directly observe within our own familiar vicinity. Furthermore, how does the fragile nucleus itself react to the immense stresses encountered during its closest approach to the Sun, its perihelion passage? Will the accumulated pressure and heat cause it to violently fragment, or will it simply succumb to a quiet dissolution, fading back into the darkness of space? And crucially, could other interstellar visitors yet to be discovered possess even stranger compositions, exhibiting behaviors entirely alien to the models and expectations we have developed based on our local observations? These unanswered questions form the driving force behind ongoing efforts. They fuel continuous observation campaigns using powerful telescopes, inspire sophisticated theoretical work attempting to model these extraordinary phenomena, and potentially point towards future missions whose very purpose is to intercept and study such interstellar objects directly. Looking toward the future, the comet known as 3II Atlas may ignite the ambition for a new generation of space exploration. Concepts are already swirling within scientific and engineering circles. These include proposals for rapid response spacecraft designed specifically for lightning-fast deployment to intercept newly discovered interstellar wanderers. Complementary ideas involve precision instruments capable of analyzing chemical and isotopic composition on the spot, and high-resolution imaging systems able to provide hyper-detailed, real-time views of the minute and complex surface features unfolding before our instruments. Unlike familiar celestial bodies within our solar system, interstellar objects offer distinct logistical and engineering hurdles. Their rapid trajectories, often diminutive size, and unpredictable appearances present formidable obstacles. Nevertheless, the scientific potential, as exemplified by the object designated Atlas, could be profoundly transformative. It grants direct investigation into distant stellar systems without necessitating departure from our own cosmic neighborhood. Furthermore, Atlas galvanizes unprecedented international scientific cooperation.
Its effective monitoring demands a highly coordinated strategy, integrating space-based observatories such as the James Webb Space Telescope, SOHO, and Hubble, with ground-based instruments distributed across numerous continents. Citizen scientists, including dedicated amateur astronomers, also meaningfully contribute to the dataset by meticulously tracking subtle variations in brightness, monitoring for potential outbursts, and observing long-term fading patterns. Atlas unequivocally demonstrates that 21st century science is inherently global, collaborative, and participatory, an enterprise where both professional researchers and enthusiastic amateurs share the privilege of witnessing and interpreting phenomena unfolding across staggering distances of billions of kilometers. Contemplating the lessons Atlas imparts, we are struck by the immense scale and intricate complexity of the universe itself. It transcends mere chemical or physical anomalies that capture our curiosity. It is the profound narrative these visitors convey about the fundamental nature of the cosmos. Atlas is a traveler, forged under alien conditions billions of years ago, its composition transformed over eons, yet arriving to intersect with our solar system. This encounter offers a fleeting, yet invaluable glimpse into processes we could otherwise only theorize about. It serves as a cosmic bridge, spanning both vast distances and immense timescales, connecting Earth with its distant point of origin through a delicate ephemeral thread composed of ice, rock, and complex molecules. Ultimately, 3 millennia of observation reinforce both humility and curiosity. It serves as a profound reminder that despite centuries of astronomical scrutiny, the universe consistently retains its capacity to surprise, challenge, and inspire. The comet Atlas transcends mere scientific inquiry. It stands as a poignant reminder of our position within a galaxy teeming with wonders utterly beyond full comprehension. Observing Atlas compels us to confront the stark limits of our current knowledge while simultaneously illuminating the boundless potential for future discovery. It instills essential qualities in every explorer, whether they traverse the stars or peer intently through a telescope on Earth, namely patience, rigorous methodology, and vibrant imagination. As Atlas recedes into the profound depths of interstellar space, its legacy extends exceptionally far beyond the raw datasets it generated. It has fundamentally reshaped scientific expectations, challenged deeply held assumptions, and powerfully reminded humanity that our solar system forms just one intricate part of a much larger, dynamic, and profoundly interconnected galactic whole. Its journey demonstrates that even amidst an era of unparalleled technological achievement, the universe still holds mysteries capable of compelling both deep wonder and profound reflection.
The enduring legacy of Atlas will not reside solely within scientific papers and observatory logs. It will persist vibrantly within the awakened imagination, rekindled curiosity, and profound sense of awe it inspired in every individual who followed its celestial path. In the final analysis, the mystery endures. Atlas has revealed phenomena that elude complete understanding, posed questions that may require decades or even centuries to answer, and ignited a deep-seated recognition of our distinct place within the vast cosmos. It serves as an enduring reminder that the universe surrounding us is not merely immense and ancient beyond measure, but fundamentally stranger and more wondrous than our most vibrant imaginations can fully conceive. Yet within this cosmic mystery lies a counterpoint of equal significance. Our innate human curiosity serves as the enduring bridge, the vital connection that spans the colossal chasm between our terrestrial home and the universe's deepest, most elusive wonders.